Some ancient stone structures have survived earthquakes for thousands of years. These monuments, built by cultures long gone, hold a secret. They were engineered to endure. This is the mystery of seismic engineering, hidden inside ancient megalithic architecture. By the end of our journey, you will understand the forgotten principles that gave these giants their legendary strength, knowledge that could reshape how we build tomorrow. How did builders without modern science design walls that flex and sway with the Earth's tremors? What did they know about stone and stability that we are only now rediscovering? The answers lie in a global conversation between humanity and a restless planet, written in a language of polygonal stones and silent, enduring mass. What does true resilience look like when it's carved in stone? A modern skyscraper is designed to bend, a calculated dance with seismic waves to avoid breaking. Yet across the globe, ancient stone complexes often do something entirely different. They simply stand. The ground may shudder, but these monuments of immense weight and puzzling assembly remain stubbornly, eerily still. This is the foundation of our mystery, the observable fact that sparks a deeper investigation. We are looking at megalithic architecture, construction using very large stones, often fitted together without mortar. And we are observing seismic engineering, the science of designing structures to withstand the forces of an earthquake. On the surface, these two concepts should be separated by thousands of years of human knowledge. The builders of these sites lived long before the formal study of physics or material science. They had no seismographs, no computer models, no reinforced concrete. And yet, the evidence written in stone suggests they achieved a level of resilience that modern engineers are only beginning to fully appreciate. This presents us with a fascinating paradox. Were the earthquake-resistant qualities of these structures a deliberate innovation, a set of secrets passed down through generations of master builders? Or were they merely a fortunate byproduct of the only construction methods available at the time, a happy accident of history? To move beyond speculation, we must first learn to see these monuments not just as sacred sites or historical artifacts, but as complex physical puzzles. Each stone, each joint, each foundational choice holds a potential clue. By defining the terms of this ancient engineering challenge, we prepare ourselves to dissect the specific, brilliant, and often counterintuitive secrets that have allowed these giants to silently defy the Earth's tremors for ages. The walls themselves hold the first secret, a technique so simple in concept, yet profound in its effect. Look closely at the most resilient ancient structures, and you will rarely find mortar holding the stones together. Instead, you see a masterful art form known as dry stone masonry. Enormous blocks, often with bizarre, irregular shapes, are fitted together like a three-dimensional stone puzzle. The joints are so tight that, famously, a razor blade cannot slip between them. Yet there is no cement, no adhesive. The only force holding this puzzle together is gravity and the perfect, interlocking friction of each unique stone against its neighbor. This is not a flaw or a limitation. It is, we now understand, a brilliant seismic innovation. When the ground begins to shake, a rigid, mortared wall wants to act as one solid unit. The seismic waves hit it, and the entire structure tries to move as a single, brittle mass. This creates immense stress concentrations at its weakest points, and it will typically crack and collapse. A dry stone wall behaves entirely differently. It is not a single unit, but a collaborative assembly. During a tremor, the individual stones are permitted to do something extraordinary. They can shift, they can rock, they can settle. They move just a tiny amount against one another. This minute movement is the key to its survival. The kinetic energy from the earthquake does not travel through the wall as a destructive force. Instead, it is dissipated, transformed into friction and heat between the countless stone interfaces. The energy is literally scrubbed away through millions of micro-movements across the surface of each block. Structural engineers and archaeologists studying these sites describe this as creating a living wall. It breathes with the earth. It absorbs the punch of a seismic wave and redistributes that force harmlessly throughout its entire network of stones, rather than letting it focus on a single failure point. The physics at work here are strikingly similar to a modern engineering solution called base isolation. In contemporary skyscrapers built in earthquake zones, engineers often place the entire building on massive rubber and steel bearings. When the ground moves, these bearings allow the building to slide and sway independently, isolating the structure from the worst of the shaking. The ancient dry stone wall is, in essence, a primitive but incredibly effective form of distributed isolation. Every stone joint acts as a tiny, natural bearing, allowing for controlled movement and energy dispersion. This was not a haphazard process. It required a deep, empirical understanding of dynamic loads, gained through generations of trial and observation. The builders carefully selected stone shapes, often using polygonal blocks with multiple contact faces. This created a more stable, interlocking geometry that could settle into a configuration after a tremor. Gravity itself was harnessed as the primary stabilizing force, with each stone's immense weight helping to lock the entire assembly back into place once the shaking stopped. A powerful illustration of this principle stands in the Andes Mountains. The fortress overlooking Peru is famed for its colossal zigzagging walls. Some of these limestone blocks weigh over 100 tons. They are fitted together with that signature, mind-bending precision. This region is one of the most seismically active on the planet. The ground here has shuddered countless times over the centuries, toppling Spanish colonial cathedrals built with mortar just below. Yet, dry stone walls remain unmoved. They have settled, they have shifted minutely, but they have not fallen. The walls flexed, and in doing so, they endured. This flexible approach to construction reveals a foundational secret, a dialogue with the earth that favored dynamic adaptation over rigid resistance. The polygonal stones themselves are a second, profound secret. These are not simple bricks or uniform blocks. Each massive piece is a unique, multifaceted polygon, shaped to fit only its specific place in the grand design. The result is a three-dimensional stone jigsaw puzzle of staggering complexity. At first glance, this might seem like an artistic choice, a display of sheer craftsmanship. But from an engineering perspective, it is a stroke of seismic genius. The irregular, interlocking shapes serve one critical purpose: they prevent the formation of straight, continuous fault lines. In a wall made of rectangular blocks stacked in neat rows, a seismic shock can create a crack that propagates cleanly along the mortar joints, splitting the structure in two with terrifying efficiency. A polygonal wall offers no such straight path. A potential crack driven by seismic force reaches a joint and is immediately deflected. It must travel diagonally, then turn, then split again at an odd angle. With each twist and turn, the destructive energy of that crack is dissipated. It loses momentum, scattering into the complex network of stone interfaces until it simply fades away. Geologists studying these structures note that the stress from an earthquake is not concentrated, but distributed across a vast, interconnected web. Every angled face, every locking corner, shares a tiny portion of the load. It is a principle of collective resilience, where the strength of the whole is far greater than the sum of its oddly shaped parts. Think of it like trying to tear a piece of crumpled paper along a straight line. The path of least resistance is gone. you are forced to fight against the material's own tangled geometry. The seismic wave meets a similar fate. Its energy is forced to travel a tortuous, inefficient path through the wall, losing power at every unexpected junction. This required a level of craftsmanship that still baffles observers today. How did ancient builders achieve such perfect fits between stones weighing tens of tons? The process likely began with meticulous selection, finding stones in quarries whose natural shapes suggested a potential fit. Then, through a laborious process of trial and error, using harder stone tools and abrasive sand, the masons would have slowly dressed each block, shaping its multiple faces to match the negative space left by its neighbors. Some researchers suggest the use of wooden molds or templates to guide the shaping, while others point to evidence of thermal techniques, where fire was used to expand, and then cool stone to make it more workable. The goal was not aesthetic perfection in our modern sense, but functional perfection, a seamless mechanical bond that would last for ages. A powerful testament to this secret stands in Peru. Here, high on a mountainside, a terraced complex features some of the most sophisticated polygonal masonry in the Andes. The stones, some rose-colored granite hauled from a quarry across a valley and a river, are fitted with that characteristic, mind-defying precision. This region is seismically active, and the site has endured. The walls do not simply resist earthquakes, they confuse them. The chaotic, interlocking pattern provides no clean line of attack for seismic force. Across the world, the ancient retaining walls of Delphi in Greece, built using similar polygonal techniques, have also withstood countless tremors in that volatile landscape. They stand not as rigid monoliths, but as dynamic stone tapestries, their very irregularity being the source of their enduring strength. This reveals a deeper layer of ancient understanding, a mastery of geometry not just for art, but as a fundamental tool for structural integrity. They engineered chaos into order, creating a resilient whole from a collection of beautifully mismatched pieces. But sheer weight alone is not enough to defy an earthquake. The third secret lies in how that weight is connected to the earth itself. This is the principle of inertia and massive foundations. Inertia is a fundamental law of physics, the tendency of an object to resist any change in its motion. A small pebble is easily kicked, but a boulder is not. Ancient builders harnessed this principle on a monumental scale by creating structures of such immense mass that the ground shaking simply could not move them. They achieved this not just by piling up heavy stones, but by forging an unbreakable bond between their creation and the planet's most stable layer, the bedrock. Engineering historians note that these cultures displayed an intuitive, yet profound, understanding of geology. They did not simply build on the ground, they sought out specific, stable sites and often sculpted the living rock itself into the first course of their construction. The process began with meticulous site preparation. Using simple but effective tools and techniques, like water-filled trenches to find a true level, they would painstakingly grade and flatten the foundation area. In many cases, they did not just level the soil, they cut directly down into the bedrock, creating a perfectly flat stone podium. This served multiple purposes. First, it prevented any uneven settling that could weaken the structure over time. Second, and most crucially for seismic resilience, it created a phenomenon engineers call a keyed base. The bottom layer of the structure's stones were not just placed on the bedrock, they were often shaped to fit into sockets or grooves carved into the rock itself. Some foundations even used a layer of compacted gravel or sand. This might seem counterintuitive, but it acts as a brilliant shock absorber and drainage layer, allowing minor shifts and preventing water from pooling and undermining the stone. The result was a single, unified mass, a mountain of crafted stone literally growing out of the mountain itself. When seismic waves arrive, they are high-frequency vibrations, the kind that easily topple a light, flexible building. But when those same waves hit a pyramid or a massive stone platform rooted into bedrock, something different happens. The incredible inertia of the structure resists the initial jolt. The energy of the earthquake is spent trying to move a mass that is effectively part of the continent. It is like trying to shake a tree by vibrating a single leaf. The effort is futile against the deep, rooted stability of the whole. A perfect example of this secret in action is the Great Pyramid of Giza. Its base covers an area of over 13 acres, and it sits on a vast, artificially leveled plateau of solid limestone bedrock. The corners of its foundation are precisely aligned to the cardinal directions, and the leveling across that immense area is so exact that the margin of error is less than an inch. This was not merely for astronomical or symbolic precision, it was foundational engineering. By creating a perfectly flat, stable base bonded to the earth, the builders ensured the pyramid's colossal weight, estimated at nearly 6 million tons, would be distributed evenly and anchored immovably. When the ground in the region has shaken over the pyramid has not swayed or flexed like a dry stone wall. It has simply stood, a lesson in monumental inertia. This massive approach to stability presents a fascinating counterpoint to the flexible, jointed walls we saw earlier. One technique embraces movement to dissipate energy. The other uses overwhelming mass and deep anchoring to simply refuse to move at all. Together, they reveal a sophisticated ancient toolkit, where the solution was tailored to the challenge, the materials, and the landscape. But what happens when the earth does not just shake, but actually rolls in a wave beneath these giants? The true test of a structure comes from above, not just the sides. A roof must hold its own immense weight while resisting the violent lateral shoves of an earthquake. For this, ancient builders developed a fourth, brilliant secret: the strategic use of corbelled arches and vaults. To understand its power, visualize a ceiling built without a single curved stone. Instead, picture flat, horizontal slabs stacked in layers, with each new layer projecting slightly inward over the one below. This continues step by step, until the gap at the top is small enough to be capped by a final stone. This is a corbelled arch, a staircase of stone reaching for the sky and then closing in on itself. It is a masterpiece of compression. Unlike a true Roman arch, which relies on a precise keystone to lock a curve in place, the corbelled arch works through sheer gravity and incremental overhang. Each stone is supported by the one beneath it, and the entire, massive weight of the roof is channeled down along a clear, vertical path through the thick supporting walls. Architectural historians point out its widespread use in places as diverse as the monumental tombs of Mycenaean Greece and the soaring temples of the Maya. The choice was not merely stylistic, it was profoundly seismic. The genius lies in its built-in redundancy. In a true arch, if the central keystone fails or shifts dramatically, the entire structure can collapse catastrophically. A corbelled arch has no such single point of failure. It is an assembly of independent, horizontal elements. If an earthquake causes one of these stone slabs to shift or settle slightly, the load above it simply finds a new path. The weight is redistributed to the neighboring stones, and the structure adjusts. It is a system designed with a margin for error, an understanding that in a dynamic world, flexibility and backup plans are the essence of survival. The construction process itself reveals this careful, empirical wisdom. Builders worked with precise geometric ratios, ensuring each inward step was calculated to maintain balance throughout the process. They built from the walls upward and inward simultaneously, a slow, patient act of creation that allowed them to monitor stability at every stage. This method stands in stark contrast to a true arch, which requires a temporary wooden framework and cannot support itself until the very last keystone is set. The Corbelled vault was self-supporting from the first stone laid, a testament to a pragmatic, step-by-step approach to defying gravity. A stunning example of this secret's endurance is the Treasury of Atreus in Mycenae, Greece, also known as the Tomb of Agamemnon. This beehive-shaped tomb, is constructed entirely using the Corbelled vault technique. For over 3,000 years, its soaring interior has remained intact, a silent, domed space in one of the most tectonically active regions in the Mediterranean. The Peloponnese is crisscrossed with fault lines, and the ground has shaken countless times. While later structures around it have fallen to ruins, the Corbelled vault of the treasury has simply settled, its stones shifting minutely into an even more stable configuration. It demonstrates a profound ancient insight into load paths, the invisible lines of force that travel through a structure. By designing a roof that funneled all forces straight down into the earth through massive walls, they created a system that was not just strong, but intelligently strong. With a built-in capacity to adapt when the earth refused to stay still, the fifth secret is a masterpiece of hybrid engineering, a conversation between stone and wood. Deep within the walls of certain ancient fortresses and temples, hidden from plain sight, lies a network of horizontal wooden beams. This technique is known as timber lacing, or sometimes cage construction. It represents a brilliant composite strategy, where two materials with opposite properties are combined to create something greater than the sum of their parts. Stone is immensely strong under compression. It can bear fantastic weight, but it is brittle and it has almost no tensile strength, meaning it cracks easily when pulled or bent. Wood, on the other hand, is flexible and possesses excellent tensile strength. It can bend and stretch before it fails. Ancient builders intuitively understood this dichotomy. By weaving horizontal layers of timber into the very fabric of a stone wall, they created a structure that was both monolithic and ductile. The rigid stone matrix provided the crushing strength, while the flexible wooden lattice acted as a built-in shock absorber. During an earthquake, the wooden beams would flex, allowing the entire wall to sway and bend as a unified whole, just enough to dissipate the seismic energy without reaching a breaking point. It was a deliberate design for controlled deformation. This principle is strikingly similar to modern reinforced concrete, where steel rebar provides the tensile strength within the compressive strength of the concrete. The ancient version used nature's own materials to achieve a comparable result. The choice of wood was not accidental. Builders selected specific species known for their durability and resistance to rot, such as cedar or certain hardwoods. In some cultures, the maintenance of these wooden elements may have been a ritualistic practice, a periodic renewal ceremony that ensured the structural and perhaps spiritual integrity of the building. Over centuries, however, even the most resilient wood will decay. This has left behind a crucial archaeological signature: empty slots and channels within otherwise solid stone walls. Restoration experts working on ancient sites in seismically active regions like Turkey or Kashmir often discover these voids. To the untrained eye, they might look like gaps or mistakes. But to an engineer, they are the ghostly imprint of the structure's original flexibility, the clear evidence of a sophisticated anti-seismic system that has long since returned to the Earth. A powerful case study of this secret exists at the capital of the ancient Hittite Empire in modern-day Turkey. The monumental walls of this city, built over 3,000 years ago, show clear evidence of timber lacing. The Hittites inhabited a land of frequent tremors, and their fortifications needed to be both imposing and resilient. The wooden beams integrated into their stonework provided that necessary give, allowing the massive defensive walls to withstand shocks that would have shattered a purely rigid construction. An even more vivid and living example can be found in the traditional construction of the Kashmir region in the Himalayas. Here, the technique evolved into a complete building system. Walls are built as a braced timber frame, with the compartments then filled with stone, rubble, and mortar. This creates a lightweight, flexible cage that has proven extraordinarily resilient in one of the world's most earthquake-prone zones. When major quakes have devastated areas with modern concrete buildings, many structures have survived, swaying with the shockwaves but not collapsing. This ancient hybrid approach reveals a profound wisdom, the understanding that true resilience is not about absolute rigidity, but about the intelligent marriage of strength and flexibility. It is a dialogue between materials, where each plays its part in a silent, enduring dance with the Earth's restless energy. Metal was the final, deliberate lock in their ancient seismic puzzle. Beyond the friction of dry joints and the inertia of mass, some cultures took a more active step to fortify their stone giants against the Earth's lateral shudders. They used metal. Not as ornament, but as hidden structural reinforcement, embedding intricate clamps and dowels deep within the stone itself. These were not simple bars. Archaeologists have cataloged a variety of sophisticated shapes, from simple I-beams to complex double T or swallowtail designs. Each meticulously carved to fit into a corresponding recess, chiseled into the faces of adjoining blocks. The purpose was brilliantly direct, to prevent the massive stones from sliding or bouncing apart during violent shaking. While the overall structure relied on gravity and compression, these metal elements provided something stone alone could not: tensile strength. They tied the assembly together, acting like hidden ligaments that allowed the structure to flex as a single, reinforced unit rather than a collection of independent parts. This required a remarkable coordination of crafts. Stonemasons had to carve the receiving channels with incredible precision, while metalworkers had to forge or cast the clamps to an exact fit. The technological sophistication speaks to a deep, practical understanding of dynamic forces. Metallurgists studying ancient sites note that the choice of material, often bronze or a primitive form of iron, was critical. These metals offered a balance of strength and a slight ductility, a controlled ability to bend without snapping, which would have been essential during an earthquake's complex motions. An even more enigmatic detail surrounds the installation. In many cases, once the metal clamp was set into its stone socket, the builders would pour molten lead around it. The reasons for this are still debated. Some researchers suggest it was primarily for corrosion protection, sealing the iron or bronze away from air and moisture. Others propose a more dynamic function. The lead, once cooled, would have created a somewhat flexible, yet secure bond. It could absorb tiny vibrations and accommodate minuscule shifts between the stones, acting as a shock-absorbing bedding that prevented the harder metal from grinding against the stone and causing stress fractures over centuries of subtle movement. This points to a nuanced understanding of material interaction, an effort to manage not just the large catastrophic event, but the cumulative wear of countless minor tremors. The evidence of this secret is etched into stone across the ancient world. At the Parthenon in Athens, though the clamps themselves were looted long ago, the distinctive swallowtail-shaped holes remain visible in the marble blocks. A ghostly blueprint of the sophisticated reinforcement that once held the temple together, in a seismically active landscape. Perhaps even more striking examples exist at the Jain temples in India. Constructed entirely of marble, these 11th and 12th century structures are renowned for their breathtaking, lace-like filigree stone carvings. This delicate beauty rests upon a hidden skeleton of iron clamps. The builders understood that the intricate, slender pillars and ornate ceilings required additional lateral stability to survive. The clamps provided that unseen strength, allowing the ethereal artistry above to endure for nearly 1,000 years. This use of metal represents a leap in intentional engineering. It moves beyond harnessing natural principles of friction and mass into the realm of creating a composite material system. The stones handled the compression, the metal handled the tension, and the lead perhaps managed the interface. It was a deliberate, material solution to the problem of lateral restraint, a clear signal that these builders were not just stacking stones, they were engineering resilience into every hidden joint. The geometry of a wall can be a silent guardian against chaos. This seventh secret lies in a simple, powerful shape, the tapered wall. From a distance, many ancient structures appear to have walls that lean inward, wider at the base and narrower at the top. This is not an optical illusion or a sign of settling. It is a deliberate seismic strategy known as batter or taper. By designing a trapezoidal or pyramidal profile, ancient builders were manipulating fundamental physics to create an almost unshakable form of stability. Civil engineers today recognize this principle instantly. It is the same geometric logic used in the design of modern massive dams and retaining walls, structures that must hold back incredible forces. The genius is in how it manages two key factors, the center of gravity and the moment of inertia. A tapered wall has its greatest mass and width low to the ground. This dramatically lowers its center of gravity, making it far less likely to tip over, much like a weighted bottom toy that always rights itself. Simultaneously, the sloped face increases what engineers call the moment of inertia, which is essentially the structure's resistance to being rotated or overturned by a lateral force like an earthquake's push. When a seismic wave hits a vertical wall, it applies a pure turning force, trying to pivot the top over the base. But when that same wave strikes a tapered wall, the physics change. The sloped face encourages the force to be resolved into two components. A portion of the energy is directed inward, compressing the wall into itself, and a larger portion is channeled downward, deep into the massive foundation. The shaking is transformed from a tipping threat into a consolidating pressure. This intuitive grasp of static equilibrium under dynamic, violent conditions is staggering. Different cultures arrived at this same wisdom, tailoring the specific angle of taper to their materials and aesthetic. The massive pylons of Egyptian temples, like those at Karnak, incline noticeably inward. The iconic step pyramids such as El-At, are essentially a series of tapered platforms stacked upon one another, each layer creating a broader, more stable base for the next. The angles were not random. They were calculated through generations of observation to find the optimal balance between monumental height and unyielding stability. A breathtaking example of this principle pushed to an artistic extreme is the Sun Temple in India. Though now in ruins, its remaining structure and detailed accounts reveal its original form. The temple was conceived as a colossal stone chariot, and its walls were engineered with a pronounced, dramatic taper. This gave the entire edifice a powerful, grounded presence, as if it were growing from the earth itself. In a region susceptible to cyclones and seismic activity, this geometric strategy was a matter of survival. The tapered walls did not just support the weight of the stone above, They actively fought against the lateral forces of nature, directing every challenge downward into the earth. This geometric secret reveals a profound dialogue between form and force. It shows builders thinking not just in terms of stacking weight, but of sculpting direction, using shape to guide the invisible energies of the planet away from their creations. The sloped wall is a gentle redirect, a way of telling an earthquake's force, not this way, but down, back into the ground from which you came. The pursuit of perfection itself became an eighth, almost obsessive secret. In the heart of these ancient walls, we find joints of such impossible precision that they defy simple explanation. Two stone faces, each weighing tons, meet with a flatness measured in thousandths of an inch. The classic description holds true. Not even the thinnest blade can find purchase between them. This flawless mating is not merely a show of skill, it is a foundational principle of seismic engineering. A perfectly flat, broad contact area between stones maximizes friction, that same force that allows our feet to grip the ground. It ensures that the colossal weight above is distributed evenly across the entire surface of the block below, eliminating any dangerous points of concentrated stress. When an earthquake strikes, this uniform bearing allows the force to travel through the wall as a distributed wave, not a focused blow. But here lies a fascinating paradox within the precision. In some of these immaculate joints, researchers and restoration stonemasons have noted something curious: the occasional presence of a deliberate, hair-thin gap. This was not an error, it was likely a calculated allowance. These microspaces could serve two critical functions. First, they might accommodate the natural expansion and contraction of stone with daily and seasonal temperature swings, preventing the immense blocks from grinding against each other and causing surface fractures, a process known as spalling. Second, and perhaps more crucially for seismic resilience, these minute gaps provided a tiny reservoir of movement. During a tremor, the stones could shift that infinitesimal amount without slamming into one another, absorbing the initial jolt before the full friction of the broad, flat surfaces engaged to halt the motion. It was a system engineered with both intimacy and breathing room. The question of how this precision was achieved with what we consider primitive tools is a mystery that captivates engineers. The process likely involved a patient, staged technique. After rough shaping, masons might have used a method called iterative abrasion. They would coat the face of one stone with a colored slurry or paste, then carefully rub the mating stone against it. The high spots where the color transferred would be ground down, again and again, until the entire surface showed uniform contact. Some theories suggest the use of finely grated sand as an abrasive, worked between the stones with water. There is also compelling evidence from sites like the Parthenon for the use of thin sheets of lead. A lead sheet hammered into the joint would conform perfectly to any microscopic imperfections in both stone faces, creating a custom-fitted, malleable interface that further distributed load and dampened vibrations. A profound illustration of this secret exists not in a wall, but in a box. Deep within the of Saqqara in Egypt lie 24 massive sarcophagi, each carved from a single block of granite or basalt. Their interiors are polished to a mirror-smooth optical flatness, with corners that are perfectly square. The precision here is so advanced that it seems to belong to another age of technology altogether. The lid of one of these giant boxes weighs an estimated 30 tons, yet it was engineered to fit its base with that same legendary, airtight seal. This was not for holding a body, but for containing something sacred, requiring an absolute barrier. The obsession with such flawless contact mechanics in a funerary context speaks volumes. It tells us that the mastery required to create a perfect seal to eliminate all points of weakness, was considered a technology of the highest order, a physical manifestation of permanence and protection. This drive for perfection in jointing reveals the final layer of the ancient builders' mindset. They understood that resilience was not just about grand shapes and massive weights, but about the invisible world of surfaces and forces at the point of contact. It was about controlling the interface, the moment where one stone meets another, because they knew that is where stability is either created or catastrophically lost. High within a temple's shadowed vault, a massive stone hangs still in the quiet air. This is not a static monument, but a potential pendulum waiting for the earth to speak. Our ninth secret ventures into the most speculative, yet captivating, idea of all, the possibility that ancient builders intuitively created harmonic mass dampers. In modern skyscrapers like the Taipei 101, engineers install a colossal tuned mass damper, a gigantic steel ball suspended near the top of the building. When wind or seismic waves cause the structure to sway, this immense weight sways in the opposite direction, its counter-oscillations canceling out the building's movement and stabilizing the whole tower. It is a masterpiece of active vibration control. Could an intuitive, passive version of this principle have been discovered ago? Some physicists and historians examining certain ancient sites propose a fascinating thought experiment. They point to architectural anomalies, like monolithic stone beams or idols that are not fully anchored, but appear poised, or chambers where local tradition speaks of stones that once hung from chains. The most cited example is found at the temple in India. Here, within the temple complex, stand 56 monolithic stone columns. Each is a single carved piece of granite. According to local lore, and demonstrated in gentle tests by archaeologists, some of these columns produce distinct musical notes when tapped lightly. They are often called the musical pillars. More intriguingly, the main columns supporting the structure's massive stone roof are not rigidly fixed to their base. They are balanced, allowing for a minute amount of independent movement. The cultural purpose was almost certainly ritual and artistic, dedicated to creating sacred sound and vibration for ceremonies. Yet the dynamic effect of such a design is undeniable. A forest of massive, freestanding stone pillars, each with a slightly different resonant frequency, would create a complex vibrational landscape during an earthquake. The energy from a tremor would not travel through the temple as a unified shockwave. Instead, it would be scattered, absorbed, and dissipated by the countless tiny movements and resonances of the individual columns. Each pillar would sway at its own pace, interfering with and dampening the coherent destructive frequency of the quake. This is not a tuned damper in the modern, precise sense, but a form of distributed vibrational damping. The builders may not have understood the physics of wave interference, but through deep acoustic experimentation, they could have empirically discovered that certain configurations of stone led to structures that felt more stable, that hummed with a certain energy, or that survived when others fell. The connection between sound and stability is profound. Managing harmonic resonance was likely a primary goal, but for spiritual and ceremonial reasons. They crafted spaces where specific chants or instruments would fill the chamber with a pure, enveloping tone, believing this connected them to the divine. In doing so, they may have inadvertently engineered a defense against the Earth's lowest, most destructive frequencies. By designing pillars and chambers that resonated with chosen sacred notes, they were essentially tuning the building to filter out chaotic, random vibrations. The Earth's random roar would be met by a temple humming with its own intentional song. This speculative secret does not require us to believe ancient engineers had textbooks on dynamics. It asks us to consider a different path to knowledge, one built on a lifetime of sensory observation. A master mason, spending decades carving and listening to stone, might develop a visceral, intuitive feel for its behavior. He would know that a certain pillar, when struck, rang clear and long, and that the wall it supported had never cracked. He would sense that a chamber with specific proportions felt calm and solid. This accumulated, experiential wisdom, passed down and refined, could lead to designs that managed vibrational energy through shape, balance, and material choice. Even if the builders explained that management in the language of spirit and sound. It invites us to listen to these ancient spaces not just with our eyes, but with our imagination, hearing in their silent stones the echo of a forgotten harmony between architecture and the trembling earth. The land itself was their final blueprint. A tenth, deeply mysterious secret lies not in the stones, but in the very ground they chose to build upon. Ancient sites of staggering resilience were rarely placed at random. They crown specific granite ridges, nestle against particular cliff faces, or rise from plains of solid bedrock. This was more than finding a flat spot. It was a sophisticated practice of geomantic placement, an art of reading the Earth's hidden energies for stability and harmony. At its heart may lie an intuitive, perhaps even ritualistic, understanding of telluric currents and geological advantage. Telluric currents are weak, natural electrical flows that travel through the Earth's crust, influenced by solar activity and the planet's own magnetic field. While modern science measures them as a geophysical fact, some speculative theories propose that ancient cultures, through practices like dowsing or deep sensory observation, could have identified zones where these energies were concentrated or calm. The choice to build on such a spot might have been framed in spiritual terms, as aligning with the breath of the earth dragon or the path of celestial forces. Yet the practical seismic benefit of such alignment could have been profound. Building directly upon solid, continuous bedrock is one of the most effective seismic strategies possible. Bedrock shakes far less violently than loose soil or sediment during an earthquake, a phenomenon engineers call ground motion amplification. Soft ground acts like a bowl of jelly, wobbling and magnifying the seismic waves passing through it. Bedrock is the firm hand holding that bowl. By meticulously selecting sites anchored to this stable foundation, ancient builders were essentially placing their structures on the platform available during the planet's tremors. The process of this sacred site selection was likely a blend of empirical observation and ritual practice. Elders or master builders might have spent days or weeks at a potential location, observing water flow, plant growth, the behavior of animals, and the feel of the ground underfoot. Techniques like dowsing, using a forked branch to detect subtle subterranean vibrations or water sources, could have identified not just aquifers, but also the solid, unbroken lithosphere beneath. An aquifer itself, a layer of water-bearing rock, presents another fascinating possibility. Some researchers suggest that the presence of a shallow water table beneath a structure can act as a natural shock absorber. As seismic waves pass through the water-saturated layer, their energy is partially dissipated, dampening the intensity of the shaking that reaches the foundation above. Whether understood through physics or simply felt as a place of good energy, the result was the same: a foundation chosen for its inherent tranquility, offers in this secret. The entire citadel is built along a narrow granite ridge high in the Andes, a spine of solid rock between two mountain peaks. The Inca engineers literally fused their architecture with this granite backbone, carving temples and terraces directly from the living stone. This placement did more than provide a dramatic view. It anchored the city to the most seismically stable feature in a landscape riddled with faults. When earthquakes ripple through the valley, the ridge moves as a single, coherent unit and moves with it, avoiding the destructive shearing that would occur on less stable ground. Across the world, the megalithic temples of Malta tell a similar story. They are strategically positioned on a plateau of dense coralline limestone, the island's most stable geological formation. This thick bedrock shelf provided an immovable base, while the temple's own massive construction provided the inertia. The builders even incorporated natural cave systems and fissures into their designs, perhaps intuitively using these features to channel groundwater or even subtle earth energies away from the structures. This profound connection to the living landscape reveals the ultimate layer of ancient seismic wisdom. It was not about conquering nature with brute force, but about listening to it, learning its rhythms, and choosing to build in conversation with the Earth's own stable bones. They sought alignment, not just with the stars above, but with the silent, powerful currents flowing deep below. In doing so, they found places where their stone giants could stand, not in defiance of the trembling world, but in harmony with its deepest, most solid self. Beneath the most enduring monuments, the earth itself was prepared to receive them. Our 11th secret reveals a foundation not of rigid lock, but of intelligent give, a layer of sand, gravel, or crushed stone meticulously placed between the structure and the solid ground. This granular cushion is one of the oldest and most effective forms of seismic isolation ever devised. At first glance, it seems counterintuitive. Why place something unstable beneath a monument meant to last forever? The answer lies in how earthquakes transfer their destructive energy. When seismic waves travel upward through solid, unbroken rock and into a rigid foundation, they pass directly into the structure with undiminished force, shaking it from its very base. A layer of loose, granular material changes this equation completely. Geotechnical engineers explain that such a layer acts as a natural shock absorber. The individual particles of sand or gravel are not bonded together. They are free to move, to settle, and to rearrange themselves minutely when energy passes through them. As the ground shakes, this granular bed absorbs a significant portion of the seismic wave's energy, transforming it into friction and heat between the countless shifting grains. The shockwave is dampened, its peak force blunted before it ever reaches the stones above. This principle is a direct ancestor of modern base isolation systems, where buildings are literally set on giant ball bearings or rubber pads to decouple them from ground motion. The ancient version used nature's own materials to achieve a remarkably similar effect. Beyond isolation, this simple technique solved another critical seismic threat: water. A carefully designed gravel layer also functions as a superb drainage blanket. During an earthquake, saturated, loose soil can undergo a terrifying transformation called liquefaction, where it temporarily loses all strength and behaves like a liquid, causing anything on its surface to sink or topple. By providing a path for groundwater to drain away from the foundation, the granular layer kept the soil beneath drier and more stable, drastically reducing the risk of this catastrophic failure. The archaeological record provides clear evidence of this deliberate practice. At the ancient Roman city of Morocco, a region of significant seismic activity, excavations of monumental buildings have revealed foundations that rest upon thick, intentionally laid beds of compacted sand and small stones. Roman engineers were masters of practical infrastructure, and this technique speaks to their empirical understanding of building for unstable ground. Even more iconic are the Colossi of Egypt, two massive stone statues that have stood on the Theban plain for over 3,000 years. While their platforms appear solid, investigations have suggested the use of foundation materials designed to accommodate the Nile's floods and the region's occasional tremors, allowing the gigantic monuments to settle evenly without cracking. This secret demonstrates a profound, practical wisdom. It shows builders thinking in terms of managing energy, not just resisting weight. They understood that sometimes the strongest connection to the earth is not a rigid weld, but a carefully mediated one, a handshake that allows for a slight, forgiving movement. By inserting a layer of humble gravel, they created a buffer zone between the chaos of the trembling ground and the serene order of their stonework above, a final, elegant filter for the planet's restless power. There is a raw, untamed power in walls built from stones that look like the bones of the earth itself. This is the domain of Cyclopean masonry, a style so formidable that later cultures could only explain it as the work of mythical giants. Far from a primitive pile of rocks, this 12th secret reveals a seismic logic of breathtaking simplicity and brute force. Visualize colossal, rough-hewn boulders, some weighing many tons, fitted together with their natural, irregular shapes intact. The joints are not razor-sharp, and the surfaces are not polished. Instead, the structure relies on an overwhelming mass and a cunning, interlocking puzzle of forms. The seismic genius here is in the creation of a high-friction, semi-cohesive unit. Each enormous stone, with its unique contours, nestles into the negative spaces of its neighbors, locked in place by its own staggering weight and the grip of countless contact points. Expert analysis of these walls shows that the builders did not leave empty gaps. The voids between the larger titans were meticulously filled with smaller chink stones, carefully selected and hammered into place. This was not filler in the modern sense. It was a deliberate act of compaction. These smaller stones acted as permanent wedges, eliminating any possibility of movement or shifting within the core of the wall. They transformed a collection of giant blocks into a single, densely packed geological mass. When an earthquake strikes, this kind of construction reacts in a fascinating way. It does not behave like a wall of neatly stacked bricks where one block can slide out, nor does it act like a rigid, mortared monolith. Instead, the entire Cyclopean assembly moves as a semi-cohesive unit. The seismic energy is distributed across the vast, irregular network of interlocking faces. The friction is so immense, and the weight so colossal, that the force required to dislodge any single stone is far greater than what a typical tremor can produce. It is a principle similar to a dry stone retaining wall, but executed on a monumental mythic scale. The structure's strength comes not from the strength of any individual block, but from the collective immovability of the whole. A powerful embodiment of this secret stands at the Lion Gate of Mycenae in Greece. The entrance to that legendary citadel is framed by megaliths so huge that their mere presence commands awe. The lintel stone alone weighs an estimated 20 tons. These are not delicate or precisely shaped. They are raw, powerful, and seemingly haphazard, yet they have guarded that threshold for over 3,000 years in one of the Mediterranean's most active seismic zones. The walls of nearby, described by the ancient poet Homer as mighty walled, are even more illustrative. They are constructed in the true Cyclopean style, with boulders of such size that their placement defies easy explanation. The walls lean inward, employing the secret of the tapered profile, and every gap is locked with those essential chink stones. This style is not unique to Greece. Across the world, in the highlands of Peru, pre-Inca cultures like the built formidable fortresses using a strikingly similar approach. At sites like Immense limestone blocks form defensive walls that seem to grow organically from the mountain. The technique speaks to a global intuition, a recognition that when facing the chaotic force of an earthquake, sometimes the most intelligent response is to build with a weight and a complexity that the earth itself cannot unravel. It is durability achieved not through delicate precision, but through the strategic application of overwhelming, interlocked mass. A slender wooden tower sways, its eaves dancing against the sky as the earth rumbles below. This is not a scene of impending collapse, but a demonstration of one of history's most elegant seismic secrets, the dynamic design of the Asian pagoda. For over a millennium, these story structures have stood in some of the world's most active earthquake zones, from the forests of Japan to the mountains of China and Korea. Their survival is no accident. It is the result of a sophisticated philosophy of controlled movement, a deliberate choice to bend like a reed rather than stand rigid against the storm. At the heart of this secret, particularly in Japanese wooden pagodas, lies a counterintuitive feature, the central pillar, or this massive trunk of wood, often suspended from the top or resting loosely on its base, is not a load-bearing column in the conventional sense. Architectural historians describe it instead as a giant, stationary pendulum. When an earthquake strikes, the flexible wooden framework of the pagoda begins to sway around this central core. This immense inertia acts as a stabilizing counterweight, its resistance to movement creating a damping effect that absorbs and dissipates the energy of the shake. It is a brilliant, passive form of harmonic control. The genius extends to every joint and bracket. The complex network of interlocking wooden brackets, known as Tokyo, is assembled without nails or rigid adhesives. These joints are designed to flex, to allow for a controlled amount of play. During a tremor, each story, with its distinct heavy roof, can sway independently from the others, almost like a stack of inverted bowls gently rocking. This independent movement prevents the building from developing a single, unified, and destructive resonant frequency. The energy from the quake is not concentrated, but scattered, transformed into friction at thousands of wooden interfaces throughout the structure. The sound during an earthquake would not be a groan of impending failure, but a soft chorus of creaks and sighs as the wood rubs against itself, literally scrubbing the destructive force away into harmless heat. This principle of damped oscillation finds expression in stone as well. The iconic stone pagodas of China and Korea, while more rigid than their wooden cousins, employ a similar seismic strategy through their iconic tiered form. Each successive level is smaller and lighter than the one below, creating a pyramidal profile that naturally lowers the center of gravity. The heavy, overhanging tile roofs at each tier act as inertial masses, helping to stabilize the structure. The layers are often built with a slight intentional separation or with flexible mortar, allowing for minute-independent settlement during a shake, preventing a catastrophic crack from racing up the entire height. A testament to this secret's enduring power stands quietly in Nara, Japan. The 5-story pagoda at the temple complex has watched the seasons turn for more than 1,400 years. Japan has endured countless powerful earthquakes in that time, yet this graceful wooden tower remains. It has swayed, it has settled, but it has never fallen. Modern engineers studying it have confirmed its dynamic behavior, the entire structure moving with a slow, graceful rhythm that defies the violent, jerking motions of the ground beneath it. This is not mere architecture, it is a dialogue with physics. It reveals a cultural wisdom that understood resilience as a dynamic, living quality. The pagoda does not fight the earthquake, it accepts the energy and transforms it, dancing with the tremor until the earth grows still again. This philosophy of bending, not breaking, represents perhaps the most advanced expression of ancient seismic thought, a lesson in humility and harmony written in wood and stone against a trembling sky. Sometimes the strongest defense is a planned retreat. This 14th secret introduces a radical idea that ancient builders may have intentionally designed certain parts of their structures to fail. The concept is known as sacrificial elements, a strategy where controlled damage in a critical area protects the vital core of the building. It is a precursor to the modern engineering idea of a fuse, a component designed to break first in order to save the entire electrical circuit. In seismic design, this principle is seen in shear walls or specially designed brittle connectors that are meant to absorb the brunt of an earthquake's energy through their own controlled destruction, thereby channeling the force away from the primary load, bearing columns and foundations. The survival of the whole is prioritized over the preservation of every single part. Seismic retrofit specialists today see clear parallels when they examine ancient sites. They note features that could have functioned as these ancient fuses. A section of wall built with slightly less mortar or a specific type of joint designed to be the first to shear might not be a construction error. It could be a deliberate weak link. The strategic placement of such an element would act like a pressure valve, allowing the pent-up seismic energy to release in a specific, manageable location. When that predetermined section cracks or crumbles, it dissipates a tremendous amount of destructive force, often leaving the foundational supports and the overall structural shell intact and stable. This invites a profound reinterpretation of damage we see at ancient sites. Take, for instance, the stepped pyramids or ziggurats where the uppermost temple or platform has collapsed, while the massive lower terraces remain perfectly solid. For generations, this was viewed simply as decay over time, but through the lens of sacrificial design, we might ask a different question. Could that collapse have been a feature, not a bug? The upper sections, often built with lighter materials or different techniques, might have been designed as a sacrificial cap. During a major seismic event, the failure of that top section could have absorbed and redirected catastrophic forces that would otherwise have traveled downward, potentially causing a total foundational collapse of the entire monument. The upper structure takes the hit, sacrificing itself so the body of the pyramid can live on. Proving this archaeologically is incredibly difficult, as it requires distinguishing between intentional design and random decay. Yet the concept itself reshapes how we view resilience. It suggests these builders thought in terms of holistic systems, understanding that you cannot always stop a force, but you can guide it. You can give it a path of least resistance that leads away from the heart of your creation. It frames damage not as a mark of failure, but as part of a deeper, more sophisticated survival strategy. This perspective turns ruins into a new kind of blueprint, where every crack and collapse might tell a story not of defeat, but of a calculated, successful defense written in stone. The stars guided their hands, but the earth reaped the benefit. A 15th secret weaves the celestial and the terrestrial into a single thread of stability. For cultures that built in alignment with the cosmos, that profound connection to the heavens may have granted an unexpected gift, a foundational resilience against the tremors below. This is the subtle influence of astronomical alignment on structural stability. Consider the immense effort required to orient a temple corridor to catch the first ray of the solstice sun, or to align a massive stone circle with the lunar standstill. The process demanded a level of surveying precision that was, for its time, nothing short of extraordinary. To achieve such a perfect celestial lock, builders first had to master the earthly plane. They needed to establish a true north-south or east-west grid with remarkable accuracy, to level vast foundation platforms, and to ensure absolute symmetry in their layouts. And structural engineers collaborating on these sites note a fascinating side effect of this cosmic ambition. A structure that is perfectly level and geometrically symmetric inherently distributes physical stresses more evenly. Its weight presses down uniformly, its walls share loads in balance, and it presents no weak, asymmetrical flank to the lateral push of an earthquake. The rigorous process of aligning with the stars forced a discipline of construction that created buildings of exceptional static equilibrium. The celestial blueprint became a recipe for earthly solidity. This connection may extend even to the timing of construction itself. A culture deeply attuned to celestial cycles would have known the seasons intimately. They would have understood the monsoon period or the harsh freeze-thaw cycles that could ruin freshly laid mortar or destabilize earthworks. By scheduling major construction phases during stable, dry seasons, guided by their astronomical calendars, they were not just following ritual, they were applying practical wisdom. They ensured their masonry cured strong and their foundations set without being undermined by water or frost, giving their creations the best possible start in life. The potential links go deeper still. Some researchers propose that the chosen alignment might sometimes correspond not just to a star, but to a geological feature like the orientation of bedrock strata, or to a dominant wind pattern that helps ventilate and dry a structure. The drive for cosmic harmony could have dovetailed seamlessly with an empirical understanding of the local environment. A powerful illustration of this secret stands at the Sun Temple in India. Built in the 11th century, the entire temple complex is a masterpiece of solar alignment. On the equinoxes, the rising sun shines directly through the temple's entrance, illuminating the sanctum. To achieve this, every aspect of its construction, from the vast step tank to the alignment of its pillars, had to be executed with meticulous geometric precision. This resulted in a structure of profound balance and proportion, qualities that inherently resist seismic forces. The temple has endured centuries in a region prone to tremors, its symmetry acting as a silent guardian. Across the world, Stonehenge presents another dimension of this idea. While its seismic resilience is less discussed than its mystery, its very existence speaks to a culture capable of staggering feats of engineering and alignment. The effort to transport those sarsen stones, to shape them, and to position them according to celestial events implies a society that could command order from chaos on a grand scale. That same organizational capability and understanding of levers, pivots, and foundations would have directly applied to creating stable, enduring monuments. The secret here is one of convergent wisdom. In seeking a bond with the heavens, these ancient builders were compelled to develop techniques of surveying, leveling, and symmetrical design that produce structures of exceptional inherent stability. Their cosmic ambition, whether intended or not, forged a powerful alliance between the sky above and the stone below, creating monuments that were harmonized with the universe and, consequently, steadfast upon the earth. Beneath the stone giants, another world flowed in silence. The 16th secret reveals that the most advanced seismic engineering was not always about stone, but about water. Ancient builders understood that to protect their monuments from the earth shaking, they first had to manage the hidden rivers beneath their feet. This was hydro-engineering as a profound seismic defense, addressing one of the most destructive forces in an earthquake, liquefaction. Picture loose, sandy soil completely saturated with water. In its normal state, it seems solid enough to walk on. But when the intense vibrations of a seismic wave pass through it, the pressure causes the water to push apart the soil particles. In an instant, the ground loses all strength, behaving like a liquid. Buildings sink, tilt, or collapse as their foundations are swallowed by this temporary, terrifying quicksand. It is a phenomenon modern engineers work tirelessly to mitigate. Astonishingly, ancient cultures developed elegant, preventative solutions ago. Their strategy was not to fight the water, but to guide it, to control the very saturation of the earth upon which they built. They achieved this through masterful, integrated drainage systems. Networks of stone-lined canals, carefully graded underground drains, and reservoirs were not mere utilities, they were the first line of seismic defense. By creating these pathways, they actively lowered the groundwater table around their most important structures, ensuring the substrate remained consistently dry and stable. This kept the soil particles in constant contact, maintaining the friction that gives Earth its strength. A powerful example of this ancient wisdom exists in the Indus Valley city of. Over 4,000 years ago, its builders constructed an elaborate, city-wide drainage system. Every house was connected to covered brick sewers that ran beneath the streets, efficiently channeling away from the foundations. In a region prone to seasonal flooding from the Indus River, this system did more than ensure sanitation. It protected the city's massive mud brick and baked brick platforms from becoming waterlogged and vulnerable to seismic failure. Similarly, in the arid landscapes of Persia, engineers perfected the Qanat, a gently sloping underground channel that tapped into mountain aquifers and transported water over vast distances to cities and farms. By providing a controlled, subterranean outlet for groundwater, Qanats prevented the dangerous accumulation of water in the building substrates of oasis settlements, making them far more resilient in a tremor. The management of water extended beyond pure drainage into the realm of ritual and mass. Within temple complexes, elaborate water features like sacred pools, bathing tanks, and fountains served a dual purpose. Symbolically, they were central to purification ceremonies, a physical manifestation of spiritual cleansing. Practically, these large, static bodies of water added significant mass low to the ground. During an earthquake, the inertia of this water would have resisted sudden movement, acting as a passive mass damper that helped stabilize the surrounding stone architecture. The maintenance of these systems, often through communal ritual cleaning, ensured the infrastructure remained functional, tying the community's spiritual health directly to its physical safety. A breathtaking demonstration of this holistic philosophy is found in Peru. This Inca site is a masterpiece of hydraulic engineering, often called a garden of water. A complex network of stone canals, fountains, and aqueducts cascades down a series of agricultural terraces. The water flow is precisely controlled, each channel an exercise in perfect balance and gravity. While its primary purpose was irrigation and display, the effect on seismic stability was profound. By managing every drop of water that entered the terrace complex, the engineers prevented erosion and uncontrolled saturation of the steep hillside. They essentially the slope against both water damage and seismic liquefaction, allowing the monumental stone retaining walls to stand firm for centuries. Even the famed Roman aqueducts, while spanning great distances, ultimately fed into urban distribution systems and drains that kept city foundations dry. This secret reveals a vision of the environment as an interconnected system. These builders saw water not as a separate element to be conquered, but as a powerful force to be understood and harmonized. By listening to its flow and directing its path, they calmed the very ground upon which their greatest dreams were built, proving that sometimes resilience is forged not in the stone above, but in the quiet. managed currents flowing silently below. A monument's true strength may be held in the hands of those who believe it is alive. Our 17th secret moves beyond stone and mortar into the realm of human spirit, exploring how psychological and ritual reinforcement became an invisible, yet vital, layer of seismic resilience. When a community believes a temple is the dwelling place of a deity, or that a fortress is guarded by the spirits of ancestors, their relationship to that structure transforms. It is no longer merely a building, it becomes a sacred trust. This profound cultural investment created the most durable preservation system of all, a legacy of vigilant, intergenerational stewardship. Anthropologists studying ancient sites note a fascinating convergence. Ritual knowledge often acted as a vessel for practical, empirical wisdom. The chants sung during a foundation ceremony might encode precise ratios for mixing materials. The dances performed to honor a completed wall could secretly teach the community the rhythm of inspecting its joints. Secret builder guilds or priestly orders held oral traditions that passed down not just spiritual lore, but the critical, hands-on techniques for repair and maintenance. A crack in a sacred wall was not merely a structural flaw, it was a spiritual breach, a sign of disharmony that demanded immediate attention. This ensured that damage from a tremor or simple weathering was addressed promptly, long before a minor issue could cascade into catastrophic failure. The structure was kept in a perpetual state of health, its physical integrity intertwined with the community's cosmic well-being. This created a powerful, self-perpetuating cycle of care. A structure believed to be divinely protected was maintained with a devotion that spanned centuries, outliving empires and weathering seismic events not just through its engineering, but through the relentless commitment of its guardians. The practical knowledge of how to repair the unique polygonal masonry, or how to ray-level a foundation slab, was preserved within ritual context, ensuring the technical secrets did not die with the original architects. The building itself became a living text, and its caretakers were taught to read its needs through the lens of sacred duty. We see this secret's enduring power in sites that have remained in continuous, adapted use. The Parthenon in Athens stands as a profound example. Its survival in a seismically active region is a tale of both stone and belief. After its time as a Greek temple, it served as a Christian church for nearly 1,000 years, and later as a mosque. Each successive culture, while altering its interior, maintained the essential shell of the structure. Why? Because it was always viewed as a place of supreme importance, a vessel for the divine, whether that divinity was named Athena, the Virgin Mary, or Allah. This continuous, reverent occupation demanded maintenance, repairs after earthquakes, and a fundamental desire to preserve the awe-inspiring form. Similarly, Angkor Wat in Cambodia transitioned from a Hindu temple to a Buddhist monastery. The spiritual significance of the site never faded, it transformed. This unbroken thread of veneration ensured that even as the jungle encroached, the core temple was never fully abandoned to the elements. Its stones cleared and its basins maintained by monks and pilgrims who saw it as a gateway to the sacred. The secret here is one of deep cultural sustainability. The most resilient structure is one that is loved, believed in, and woven into the identity of a people. The ceremonies that consecrated the stone also consecrated the community's responsibility toward it. This intangible bond between belief and mortar created a stewardship model that could last for 1,000 years, ensuring that when the earth shook, there were always hands ready to mend what was broken. Guided by traditions that remembered how, the most profound secret may be that there was no single secret at all, but a slow, patient conversation with catastrophe. Across countless generations, master builders stood amidst the rubble of a fallen temple or a cracked fortress wall. They did not have textbooks on wave dynamics, but they had eyes and they had memory. They observed which corners sheared off, which foundations settled unevenly, and which oddly shaped stones still held firm when everything around them had turned to dust. This was the 18th secret, the immense power of empirical knowledge gathered across. The seismic engineering we admire was not born from a sudden theoretical breakthrough, but from the relentless, iterative process of trial and error. Historians of technology often describe pre-industrial innovation not as a series of brilliant leaps, but as a glacier, moving imperceptibly slow, carving its path through the landscape of possibility by sheer persistent force. Each earthquake was a brutal, unplanned experiment. The structures that collapsed were the failed prototypes. Their lessons were written in broken stone, and they were lessons that could not be ignored. The techniques that survived, the polygonal joints, the tapered walls, the timber lacing, did so because they proved their worth not in an architect's model, but in the unforgiving reality of a trembling continent. This process literally edited the architectural record. In regions of intense seismic activity, we see certain construction styles vanish from the archaeological layers after a major event. The methods that led to catastrophic failure were simply abandoned, while the resilient designs were replicated, refined, and passed on. It was evolution in stone, where survival was the ultimate mark of fitness. This knowledge did not stay locked in one valley or one culture. Through migration, trade, and conquest, successful techniques traveled. A builder from a shaken city might carry the memory of a standing wall to a new land, where local artisans would adapt the principle to their own materials and traditions. The seismic wisdom of the Andes, with its flexible dry stone masonry, speaks a different technical language than the wooden pagodas of Japan, yet both are fluent in the same profound understanding. To yield is often to endure. A powerful illustration of this century's long learning curve can be traced in the church architecture of Italy, a land straddling massive fault lines. The early Romanesque churches, with their thick, rigid walls and rounded arches, were vulnerable. When the earth shook, these monoliths often cracked and fell. Over centuries, observation of these failures led to subtle, then dramatic, changes. The Gothic style introduced pointed arches and flying buttresses, which channeled forces more dynamically. Later, Baroque architects in Sicily, faced with constant tremors, developed even more ingenious flexible systems. They used lightweight volcanic stone for upper levels, inserted hidden wooden chains to tie walls together, and designed bell towers with more forgiving foundations. Each style represented a generation learning from the collapse of the last, a slow accumulation of wisdom written in mortar and faith. This reframes ancient engineering not as a static set of rules, but as a living, adaptive process. It was a dialogue with disaster, where every collapse asked a terrible question, and every surviving wall whispered an answer for the next generation to hear. The true blueprint was not on parchment, but in the collective memory of those who built, watched, and built again. The stones themselves may have been taught to sing. Within the silent, shadowed chambers of certain ancient sites, sound does not simply fade, it transforms. This 19th secret explores the integration with the natural acoustic landscape, a frontier where architecture, ritual, and physics converge in a resonant hum. The study of sound in archaeological contexts reveals that some megalithic builders did not just create spaces to be seen, they engineered them to be heard. At the Hypogeum in Malta, an underground labyrinth carved from solid limestone over 5,000 years ago, something remarkable happens. Specific chambers resonate powerfully at a frequency close to 110 Hz, a deep, vibrational hum. When a person speaks or chants within this space, their voice is altered, amplified, and imbued with an otherworldly quality. Researchers conducting acoustic measurements have confirmed these properties, noting that the architecture itself acts as a sophisticated sound filter. The question this raises for our seismic mystery is profound. Could the deliberate manipulation of sound have served a purpose beyond ceremony? Could it have been a method to manage vibrational energy of a far more destructive kind? Physicists studying structural dynamics note a fundamental principle. Every physical object, from a wine glass to a cathedral, has a natural resonant frequency. If you match that frequency with an external vibration, you induce resonance, causing the object to vibrate with increasing, often destructive, amplitude. This is how an opera singer can shatter glass with a sustained note. An earthquake produces a spectrum of such vibrational frequencies. The speculative application here is fascinating. If ancient builders, through deep acoustic experimentation, identified the resonant frequencies of their own stone chambers, they might have then used architectural shape to alter them. By designing spaces that amplified specific, safe frequencies, perhaps through chant or ritual instrument, they could have effectively tuned the building away from the dangerous, chaotic frequencies produced by seismic activity. The structure's natural acoustic response would be anchored to a chosen, harmonious note, making it less likely to sympathetically vibrate with the Earth's destructive roar. This is not about sound stopping an earthquake, but about sound shaping the structure's very identity, making it deaf to certain vibrations and receptive to others. The placement of stones within these chambers adds another layer. Projecting corbels, curved walls, and niche-like recesses are not merely decorative. Acoustic models suggest they act as primitive sound diffusers and waveguides, breaking up standing waves and preventing the buildup of energy in any single spot. In a seismic event, this same complex geometry would scatter destructive vibrational waves, preventing a coherent, building-shattering resonance from forming. The Great Neolithic Mound in Ireland offers another clue. Its long, narrow passageway, aligned to the winter solstice sunrise, also functions as a resonant tube. Sound made at the entrance is channeled and focused into the central chamber. While its purpose was likely ritualistic, to amplify the voices of the participants or to create an immersive sonic experience, the effect on vibrational stability is worth considering. A structure designed to efficiently channel specific sound waves is, by its very geometry, managing vibrational energy. It creates a preferred path for waves to travel, a path that could, in theory, guide and dissipate harmful seismic frequencies along a non-destructive route. This secret lives in the realm between documented phenomenon and inspired hypothesis. We have solid evidence that these spaces possess extraordinary acoustic properties intentionally crafted by their builders. The step from sacred sound to seismic stabilization is a speculative leap, yet it is a leap grounded in a unified principle, the ancient quest for harmony. These builders sought harmony with the cosmos, with the divine, and with the very forces of the earth. In sculpting chambers that sang with their rituals, they may have inadvertently, or perhaps quite deliberately, composed a silent hymn of stability, tuning their stone giants to a frequency of enduring peace. The final secret may have crumbled to dust long ago. Between the titanic stones of the most puzzling ancient sites, we sometimes find no trace of mortar at all. Yet the perfection of their joints whispers of something more than just masterful stonework. This leads us to a 20th and profoundly elusive secret, the legacy of lost binding materials. We must visualize a substance that is not the weak, brittle cement we might imagine, but something far more sophisticated, a complex composite with unique, almost living properties. This is the mystery of ancient mortars and binders, a material science that may have vanished, leaving only its perfect stone children behind. The ongoing debate among materials, scientists and archaeologists centers on samples taken from sites like the Great Pyramid or certain Andean walls. Analysis sometimes reveals traces not of simple lime mortar, but of compounds containing ash, specific clays, and organic additives. These are not mere glue, they are engineered interfaces. The insight from modern labs is revolutionary. A rigid mortar, as we use today, creates a brittle bond that cracks under seismic stress, transferring destructive force directly through the wall. But a mortar formulated with certain silicates and organic compounds could behave differently. It might cure with a degree of elasticity, creating a flexible, shock-absorbing layer between stones. This layer would allow for the minute, grinding movements of an earthquake, dissipating energy as heat within the binder itself. Before the stones ever felt the need to shift, the bond would breathe with the structure. We see a famous descendant of this idea in Roman concrete, a material so durable it has survived too in seawater. Its secret, recently uncovered by scientists, involves a specific mix of volcanic ash, lime, and seawater that creates a crystalline structure capable of actually healing its own cracks. When a tiny fracture forms, water seeping in reacts with the unused ash, forming new minerals that fill the gap. This self-healing property is a game changer for longevity. The question that haunts researchers is whether this was a Roman innovation or the refinement of a much older, global understanding. Could earlier cultures have developed their own versions of reactive, resilient binders? At a site like Puma in Bolivia, the puzzle deepens. Here, andesite and granite blocks are cut with machine-like precision, featuring interlocking channels, perfect right angles, and surface finishes that seem impossible for hand tools. Crucially, many of these blocks show no visible mortar residue in their joints. The mainstream explanation is that they were fitted using the same dry stone principle we have explored. But the extreme precision has led some to speculate about a different possibility. What if the builders used a thin, slurry-like binder that acted not as a gap filler, but as a lubricant and setting agent? A slurry, pourable, and then chemically set, could explain how these immensely heavy, complex blocks were aligned so perfectly during construction. Once cured, this material might have been designed to erode or degrade over centuries, leaving behind the illusion of a purely mechanical fit. The true secret, then, might be one of temporal disappearance. The most advanced part of their engineering, the intelligent matrix that held everything together, was designed to vanish, leaving only the timeless stones as its testament. This shifts our entire perspective. We have been searching for resilience in the shapes of the stones, but perhaps a crucial chapter of the story was written in the chemistry of the space between them, a chapter now faded to dust. Waiting for science to translate its lost formula, a sacred circle drawn in the sand holds a quiet, perfect strength. This 21st secret reveals that the most enduring ancient structures were often maps of the cosmos, their blueprints drawn not from mere utility, but from a profound language of symbolic geometry. When a temple's ground plan is conceived as a mandala, a representation of the universe itself, every line and angle carries a dual meaning, both spiritual and startlingly practical. Architectural historians studying these sites observe a fascinating convergence. The shapes most revered for their cosmic symbolism, the circle, the square, the triangle, and their intricate combinations, also possess inherent, formidable static strength. The quest for sacred perfection inadvertently engineered physical resilience. This is the hidden power of sacred geometry. Consider the golden ratio, a mathematical proportion found throughout nature, from the spiral of a seashell to the arrangement of leaves on a stem. In architecture, this ratio, approximately 1.618 to 1, creates rectangles that the human eye perceives as inherently balanced and beautiful. But this balance is not merely aesthetic, it is structural. A building proportioned according to the golden ratio naturally distributes loads in a harmonious way, avoiding awkward stress concentrations that could become failure points during an earthquake. The builders may have sought this proportion because it felt divinely inspired, because it echoed the growth patterns of life itself. In doing so, they were tapping into a deep code of natural stability, building in resonance with patterns that are fundamentally sound. The almond-shaped space created by the overlap of two circles of equal radius is another potent symbol, representing the intersection of the spiritual and material worlds. In architectural planning, this shape naturally generates a series of harmonious ratios and angles that guide the entire design. A structure laid out from this sacred starting point tends towards symmetry and proportional coherence. Symmetry, as any engineer will attest, is a cornerstone of seismic resilience. An earthquake's force attacks weakness, and an asymmetrical building, with one wing heavier or one wall longer, will twist and tear under that lateral load. A symmetrical, proportionally balanced temple, conceived from a sacred geometric seed, presents no such obvious flaw, its form resisting the twisting motion of the ground. We can see this geometric rigor etched into stone across continents. The layout of a classic Hindu temple is governed by the mandala, a precise square grid that maps the cosmos and positions the temple as the body of a cosmic being. Each square is assigned to a specific deity or cosmic force. This is far more than a symbolic exercise. The mandala dictates everything from the overall footprint to the placement of pillars and walls, resulting in a plan of extraordinary geometric discipline. This rigid grid ensures load-bearing walls are evenly spaced, creating a structure of remarkable balance that can withstand lateral forces from any direction. The temple becomes a stable, ordered universe in miniature, its symbolic order granting it physical fortitude. Gothic cathedrals in Europe, while expressing a different faith, pursued a similar geometric divinity. Their soaring naves and vaults were laid out using the same geometric principles found in ancient texts, often based on the square and the circle. The complex tracery of a rose window is a fractal masterpiece of sacred geometry, but it also serves to stiffen and distribute the weight of the stone frame around it. The quest to fill spaces with divine light led to a stone skeleton of incredible geometric intelligence. Perhaps no building better embodies the unity of symbolic and structural genius than the Pantheon in Rome. Its interior is a perfect sphere embedded within a cylinder. The height from the floor to the top of the dome is exactly equal to the diameter of the dome's base. This perfect geometric harmony was a symbolic representation of the heavens, the dome a concrete image of the celestial vault. Structurally, this spherical form is a marvel. The dome's thickness decreases as it rises, and its interior is coffered, both reducing weight and adding rigidity. The oculus at the apex, the building's only source of direct light, is also a relieving stress at the dome's most vulnerable point. The Pantheon has stood for nearly 2,000 years, surviving tremors that leveled other Roman monuments, not in spite of its symbolic form, but because of it. The geometry chosen to honor the gods created a shape of sublime physical equilibrium. This secret invites us to see these ancient plans with new eyes. The mandala was not just a meditation diagram, it was a stress distribution map. The sacred ratio was not just a mystical number, it was a formula for balanced loads. In seeking to build a home for the divine, these ancient architects discovered that the most sacred shapes were also, fundamentally, the strongest. Their cosmology, written in stone, became an unspoken treatise on the geometry of stability, proving that sometimes, to touch the heavens, you must first master the perfect circle on the earth. A wall's greatest enemy is not the weight above, but the push from the side. This 22nd secret lies in the strategic use of buttresses and flying supports, a brilliant idea that began not with medieval stonemasons, but in the ancient world's struggle to keep its tower standing. The principle is simple, yet profound. When a tall structure is shaken by an earthquake, the force tries to push the walls outward to make them bulge and then topple. A buttress is an external mass of masonry built directly against the wall to absorb that lateral thrust, to shoulder the push so the wall itself does not have to. It is architecture admitting it needs help, and then engineering that help into a form of rugged beauty. Construction historians trace the evolution of this idea from its most basic, brute force beginnings. The earliest buttresses were little more than massive earthen ramps or steeply sloping stone platforms piled against a vulnerable wall. They worked through sheer, grounded mass, holding the wall in place like a bookend. But over centuries, observation and innovation refined this crude tool into something more elegant and efficient. The breakthrough was understanding that the support did not need to be a solid block. It could be an articulated arm, transferring the force along a clear, arching path down into a separate pier anchored deep in the earth. This externalization of support was revolutionary. It meant the main wall could be built taller or even slightly thinner because it no longer had to bear all the lateral forces alone. The wall gained a partner, a dedicated element whose sole job was to stand firm against the earthquake's shove, allowing the wall to flex and sway without reaching its breaking point. We can see the early whispers of this idea in the enigmatic towers of Sardinia. These Bronze Age stone fortresses, some rising over 60 feet, often feature thick, sloping bases that taper upward. This is not merely a stylistic choice, it is a proto-buttress in action. The massive, broad base absorbs and redirects lateral forces deep into the ground, stabilizing the narrower tower above. The entire structure is, in essence, its own buttress, a single tapered form designed to resist overturning. Across the ancient world in Mesopotamia, the towering ziggurats employed a different but related strategy, the step back. Each successive terrace was smaller than the one below, creating a series of giant, recessed platforms. Each of these setbacks acts as a continuous, ring-like buttress for the level above. The lateral force from an earthquake hitting the upper shrine is transferred down through this cascading series of supports, each broader platform providing a wider, more stable base to dissipate the energy. It is buttressing through geometry, baked into the very form of the monument. The gradual refinement of this concept reveals a dawning understanding of moments and leverage, the physics of how a force applied at a height can create a turning effect. By moving the supportive mass away from the wall and connecting it with an arch, later builders increased the leverage of that support, allowing a smaller, strategically placed pier to do the work of a much larger, attached mass. This set the stage for the Gothic flying buttress, where the support truly takes flight, a stone arm leaping through space to channel forces with breathtaking efficiency. The ancient versions were cruder, but the intelligence was the same, to give a wall a fighting chance against the invisible, relentless push of a trembling earth. This evolution from solid ramp to articulated arm shows a deepening dialogue with physics. It was no longer enough to simply be heavy. You had to be smart about where you placed that weight. The buttress became a dedicated anatomical feature, a shoulder or an arm braced against the storm, proving that sometimes, to help something stand alone, you must first build something strong beside it. The stories told around ancient fires may have held blueprints for survival. Long before written engineering manuals, humanity's deepest technical knowledge often traveled wrapped in the cloak of myth and legend. This 23rd secret asks us to listen to these old tales not just as fanciful explanations for the world, but as potential vessels for seismic wisdom. Where practical instructions for enduring a trembling earth were encoded in the language of gods and heroes. Comparative mythologists point to a fascinating pattern found across cultures that inhabit volatile landscapes. They often feature powerful deities or beings described as earth shakers, entities whose anger or movements cause the ground to fracture and mountains to fall. Poseidon in Greek mythology was not just god of the sea, but the earth shaker, his trident striking the land to bring forth earthquakes and springs. In Japanese tradition, the massive catfish writhes beneath the islands, causing tremors when not restrained by the god. These are not random inventions. They represent a profound cultural observation, an attempt to personify and explain the terrifying, capricious force of seismicity. More importantly, these myths are frequently paired with a counter-narrative, the story of the world pillar or the culture hero. This is the figure, often a trickster or a wise teacher, who provides the knowledge to live in such a world. In some North American indigenous traditions, stories tell of a great flood or shaking earth, after which the people are taught by Spider Woman or Coyote how to build their homes in specific stable ways, often using materials and patterns found in nature. The myth becomes a memory palace, where the terrifying event of the earthquake is linked to the practical solution for surviving the next one. The building instruction is not a separate technical document, it is embedded within the survival story itself. This encoding likely served multiple vital functions. First, it ensured the information was memorable. A dry list of construction ratios is easily forgotten, but a dramatic story about a god's fury and a hero's clever response sticks in the mind, passed from elder to child across countless generations. Second, it gave the knowledge sacred authority. Telling a community to build with interlocking stones because it works is one thing. Telling them to build that way because it is the method given by the ancestral hero who saved the people from the earthshaker's wrath carries immense weight. It transforms a practical technique into a sacred obligation, a ritual practice essential for the community's continued existence. The taboos often found in these traditions further reinforce the engineering principles. A legend might forbid building on certain types of soil, or decree that a specific tree must be used for the central post of a house. To the modern ear, this sounds like superstition. But when we cross-reference these taboos with geology, a compelling picture emerges. The forbidden soil might be loose, sandy ground prone to liquefaction. The mandated tree might be a species known for its deep roots and flexible wood, perfect for withstanding lateral shocks. The taboo acts as preserving a critical piece of empirical knowledge by wrapping it in the unbreakable law of tradition. We see a beautiful, specific example in the Andes. Inca legends surrounding the construction of sites speak of a magical plant, whose juice could soften the great stones, allowing the builders to fit them together like clay before they hardened back into rock. Archaeologists and engineers obviously find no evidence of such a plant, but the story is not a literal history, it is a metaphorical one. It preserves the awe felt by later generations, who could not fathom how their ancestors achieved such perfect fits. More importantly, it encodes the central, vital principle: the stones must fit together with a seamless, almost liquid unity. The story ensures that even if the technical skill is lost, the ideal of that perfect, jointless bond is never forgotten. It keeps the goal alive in the cultural imagination. Similarly, Polynesian navigation chants, which are essentially mythic poems, contain precise star courses and wave pattern descriptions disguised as stories of ancestral voyages. The knowledge of how to read the ocean is preserved in song. It is not a leap to consider that building knowledge for their earthquake-prone Pacific islands might have been preserved in the same way. Within chants about the god of the earth and the hero who first lashed the house post securely, these narratives were a living database. The elder reciting the myth was not merely entertaining, they were transmitting a survival package. With each telling, the community rehearsed the nature of the threat and reinforced the prescribed response. The rhythm of the story, the repetition of key phrases about fitting stones or choosing a site, hammered the principle into collective memory. This reframes our understanding of these ancient sites. They are not just the product of engineering, but of mythology made manifest. The temple is the physical prayer, the built expression of a story that says, "This is how we stand firm when the world shakes." The stones themselves become the final verse in an epic poem about resilience, a poem that began long ago, whispered beside a fire under a star-filled, trembling sky. A shared tremor may have traveled faster than any caravan. Across the vast expanse of the ancient world, from the cloud forests of the Andes to the sun-bleached islands of the Aegean, builders arrived at eerily similar answers to the same violent question. This 24th secret reveals a silent dialogue of stone, the cross-cultural exchange of anti-seismic techniques. The great trade routes, like the Silk Road or the maritime paths of the Indian Ocean, did not just transport silks, spices, and precious metals. They also carried something far more valuable and intangible: the tacit knowledge of survival, passed between master masons in bustling port cities and whispered around the fires of remote caravanserais. When we see polygonal masonry in both the walls of Mycenae and the terraces of, or metal clamps used to bind stone in both the Parthenon and the temples of India, we are witnessing more than coincidence. We are seeing the fingerprints of a global conversation about how to stand firm on a trembling earth. Historians of science and technology point to a fascinating process of diffusion. Skilled craftsmen were highly mobile assets in the ancient world. A master builder from a city recently shattered by an earthquake might travel to a new kingdom, offering his hard-won expertise. He would bring not just his hands, but his memory of what worked and what crumbled. These artisans were the original vectors of engineering innovation, their knowledge embedded in practice, not parchment. They shared solutions to the universal problem of seismic force, adapting core principles to local materials and aesthetics. The trapezoidal shape, for instance, emerges as a recurring seismic motif. The trapezoidal doorways and windows found in Inca architecture are celebrated for their aesthetic and symbolic power, but they are also brilliant seismic features. Their sloping sides directing weight downward and preventing the formation of stress concentrating right angles. Remarkably, this same trapezoidal form appears in the architecture of ancient Egypt, Mesopotamia, and even in the traditional wooden frames of Japanese temples. It is a geometric solution so fundamental to stability that it seems to have been rediscovered, or perhaps shared, across multiple seismic frontiers. This presents us with a captivating puzzle for the modern mind. Were these parallel innovations, a case of convergent evolution where different cultures, facing the same environmental pressure, independently arrived at the same brilliant solution? Or does the specificity of some techniques point to a deeper, more direct exchange? The evidence invites us to consider a spectrum of possibility. Some concepts, like the simple wisdom of building on bedrock or using a tapered wall, are so logically rooted in physics that they likely sprang up independently wherever people built in earthquake zones. It is the architectural equivalent of multiple cultures inventing the wheel. However, other techniques bear a more distinctive signature. The use of swallowtail-shaped metal clamps, for example, is a highly specific technological choice involving mining, smelting, and precise stone carving. Finding this same complex system in the Mediterranean and in South Asia suggests a stronger possibility of knowledge transfer, perhaps through the slow, indirect relay of ideas across many generations and many middlemen. A technique might travel from Greece to Persia, be adapted there for centuries, and then slowly filter eastward with traders and migrants, its origin story fading into myth long before it reached a new continent. This movement of ideas shatters the illusion of ancient isolation. It reminds us that these master builders were part of an informal, global guild, connected by the shared language of practical problem solving. A merchant might not understand the physics behind the flexible walls of a Kashmiri house, but he could see they stood when others fell. He could describe them, in rough terms, to a city planner in another quake-prone region halfway across the world. The knowledge flowed slowly, over centuries, but it flowed. It transformed as it traveled, merging with local beliefs and materials. The timber lacing of the Hittites might inspire the wooden skeletons of houses in Central Asia, which in turn could influence the braced frames of structures in the Himalayas. Each culture put its own stamp on the principle, but the core insight remained, to combine rigidity with flexibility. This secret ultimately reframes our entire understanding of ancient seismic engineering. It was not a collection of isolated, mysterious triumphs, but a collaborative human project. It was a network of wisdom, woven across continents by the movement of people, goods, and ideas. The solutions encoded in stone or in the pagodas of Kyoto were not just local answers, but contributions to a vast, collective dialogue. Our ancestors were talking to each other, across mountains and oceans, and their medium was the silent, enduring strength of the stones they left behind. The proof of these ancient secrets is no longer found only in their silent endurance, but in the hum of a supercomputer. Modern engineering has begun a meticulous conversation with the past, using tools our ancestors could never have imagined to finally understand the genius they could never fully articulate. This is the 25th secret, the scientific verification through simulation and modeling, where digital worlds are built to test the resilience of stone giants. In laboratories from Lima to Kyoto, engineers are creating precise digital twins of ancient structures. Using ground-penetrating radar to see beneath the soil and laser scanners to capture every minute imperfection in a stone's surface, they build a perfect virtual replica. Then they subject it to the virtual fury of a simulated earthquake, watching as lines of colored light trace the invisible paths of stress through the digital stone. This process, known as finite element analysis, allows researchers to apply forces, measure displacements, and identify failure points without ever touching the sacred site. It transforms architectural mystery into quantifiable data. One structural engineer working with the Conservation Institute described the experience as watching a ghost perform a dance it has known for 1,000 years. The models reveal with stunning clarity what we have long suspected. When seismic forces are applied to a model of a typical mortared wall, The stress maps show bright, concentrated lines of red at the corners and joints, the precise locations where real-world walls crack and fail. But when the same forces are applied to a digital model of, say, an Inca polygonal wall, the screen tells a different story. The stress does not concentrate. Instead, it scatters like light through a prism, flowing in a diffuse, shimmering web across the entire face of the wall. The energy is shown being harmlessly dissipated across thousands of interlocking stone faces, just as the theory of dry stone masonry predicts. The simulations provide even more surprising insights. Some models suggest that these ancient walls do not perform best when they are perfectly pristine. Instead, their seismic resistance can actually improve after they have sustained minor, initial damage. A small shift or settlement from a past tremor can cause the stones to settle into an even more interlocked, stable configuration. The wall learns from the earthquake, adapting its geometry to become stronger for the next one. This finding has profound implications for conservation, suggesting that not all visible damage is a threat to structural integrity, and that sometimes the patina of time itself contributes to the monument's ongoing resilience. Another revelatory application of this technology is in understanding foundations. By using ground-penetrating radar to map the substructure of a site, researchers can model how seismic waves travel through the specific geology beneath it. They can see how a layer of gravel or a bedrock socket alters the frequency and amplitude of the shaking before it even reaches the walls above, providing concrete proof for the ancient wisdom of site selection and foundation preparation. This scientific lens is doing more than just confirming old hypotheses. It is uncovering new layers of sophistication. It allows engineers to tweak variables in the model, asking what-if questions that history cannot answer. What if the mortar was slightly more flexible? What if the timber lacing used a different wood? These digital experiments are revealing the optimal parameters for seismic resilience, parameters that ancient builders seem to have approached through generations of trial and observation. The gap between intuition and engineering is closing, not because the ancients are being demystified, but because our tools are finally becoming sensitive enough to measure their silent, stone dialogue with the earth. We are learning that their greatest secret was not a single trick, but a deep, systemic language of stability, one we are now beginning to decode, not from scrolls, but from the very stress patterns dancing across our screens. That stark image of a collapsed concrete tower beside a standing temple reveals a fundamental clash of philosophies. The modern world builds with rigid frames, a skeleton of steel or reinforced concrete designed to be ductile, to bend without breaking long enough for people to escape. This approach prioritizes life safety above all else, a noble and essential goal born from painful lessons in urban density. A seismic design professional will explain that the building is engineered with sacrificial weak points, like specially designed joints that are meant to deform, to absorb the earthquake's energy through controlled damage. The structure may be left leaning, cracked, and uninhabitable, a total economic loss, but it should not pancake. This is the critical trade-off, saving lives but often sacrificing the building itself. The ancient approach we have been exploring operates on a different principle entirely. It is not about designing for a controlled failure, but about designing to avoid failure altogether. Its resilience is built on distribution, redundancy, and a deep integration with natural forces. Where a modern skyscraper has a centralized load-bearing skeleton, an ancient polygonal wall has no central skeleton at all. Its strength is everywhere and nowhere, distributed across every interlocking stone. If one joint is stressed, 100 others stand ready to share the load. There is no single point of catastrophic failure because the system is inherently redundant. This difference extends to the materials themselves. Modern reinforced concrete is a composite marvel, but it is fundamentally brittle. Under extreme tension, it cracks, relying on the steel inside to hold it together. Once those cracks propagate, the structural integrity is compromised, even if it remains standing. Ancient monolithic stone, especially in those immense, interlocked blocks, behaves more like a single gigantic bone. It handles compression superbly, and when fitted with perfect joints, it resists tension through friction and geometry. The contrast is not about one being better, but about them being different answers to the same violent question. The modern answer is optimized for the crowded city, where saving human life is the only metric that matters. The ancient answer was optimized for eternity, for creating a legacy in stone that would outlast dynasties and speak across. One philosophy accepts severe damage to preserve life, the other seeks to prevent damage to preserve meaning and memory. This comparative analysis is not an exercise in nostalgia, it is a source of crucial lessons. Today's most forward-thinking engineers are not looking to replace steel and concrete with granite blocks. Instead, they are looking to create hybrid designs that learn from the past. Could we design buildings with distributed damping systems that mimic the energy dissipation of a dry stone wall? Could we use advanced composite materials that offer both ductility and the monolithic resilience of stone? Could our foundations be smarter, more like a conversation with the bedrock than a conquest of the soil? The ancient secrets offer a reminder that resilience can be a holistic, embedded quality, not just a list of safety codes applied to a rigid frame. They challenge us to think beyond preventing collapse and toward creating structures that can meet the Earth's tremors with a silent, enduring grace. But the stone record is not a simple textbook. For every elegant solution, there exists a confounding exception, a crack in the theory itself. An archaeologist working in a seismically active valley points to a wall built by a later, less skilled culture, its mortar crude and its stones uneven. Yet after the last major tremor, this clumsy wall stands, while a nearby section of legendary, perfectly fitted polygonal masonry shows a fresh, jagged fracture. This is the domain of the unsolved puzzle, where the established secrets meet their limits and the mystery deepens. Field researchers quietly share these anomalies, cases where the expected seismic damage is absent or appears in baffling, selective patterns. They remind us that our understanding is a map, and the territory of ancient resilience still holds uncharted lands. One variable we may underestimate is the hyper-local nature of an earthquake's fury. The direction of the seismic wave, the specific frequency of the shake, or a tiny difference in the soil's compaction under one section of a foundation can mean the difference between standing and falling. A wall might survive not because of its construction alone, but because the ground beneath it simply did not move as violently. Similarly, unknown human interventions, long lost to history, could explain anomalies. Perhaps that surviving crude wall was secretly reinforced centuries ago with a hidden timber brace, now rotted away, leaving no trace except its enduring effect. Consider the silent, imposing platforms of Easter Island, the Ahu upon which the great statues once stood. This is a landscape shaped by volcanic activity, yet many of these massive stone platforms show remarkably little evidence of catastrophic earthquake damage. Given the island's isolation and the scale of the statues, this is puzzling. Some researchers suggest the very design of the Ahu, with their inward-sloping faces and careful use of rubble fill, may have provided a stable, flexible base that dissipated energy. Others point to the possibility that the most severe damage we would expect might have been misinterpreted, that fallen could be the result of social conflict or gradual erosion, not a single seismic event. The evidence here is silent, refusing to give a clear answer. Across the Mediterranean, the ruins of Roman cities present another selective mystery. In the same quake, one temple might be reduced to a heap of column drums, while another, seemingly identical in design and materials, suffers only a cracked pediment. Modern seismic engineers modeling these sites sometimes find the results contradictory. The surviving structure might have benefited from a fortunate alignment with the fault's rupture direction, or its foundation might have been built over a particularly dense section of bedrock. There is also the ghost factor of maintenance. A building kept in constant repair by a devoted community over 500 years will enter a major seismic event in a far stronger state than its neglected neighbor, even if they were built by the same hands. These persistent gaps in the puzzle are not failures of science, but invitations. They ensure the story of ancient seismic engineering remains alive, compelling us to look closer, to question our assumptions, and to listen more carefully to the subtle language of stone and soil. For every secret we decode, the past quietly holds another, waiting in the shadow of a wall that should have fallen, but did not. A modern conservator's hand hesitates above a crack in a 1,000-year-old wall. The mortar has turned to dust, and the next tremor could be the one that finally brings this section down. The choice seems simple: fill the gap and save the monument. But the material in the conservator's trowel is not a neutral paste. It is a decision that will echo for centuries. This is the 28th secret, the profound ethical dilemma of restoration and preservation, where the very act of saving these ancient structures can unwittingly erase the seismic wisdom they were built to embody. The core conflict is stark. Do we prioritize preserving the original, authentic fabric of the monument at all costs, or do we intervene to ensure its structural safety for future generations? This is not a theoretical debate. It plays out at sites worldwide, where the pressure to keep historic sites open and safe for visitors often pushes restorers toward quick, strong fixes. The danger lies in applying modern engineering logic to ancient dynamic systems. Using a rigid, high-strength cement to repoint the joints of a dry stone wall, for instance, would be a catastrophic mistake. It would bind the living, flexible assembly into a single brittle unit, creating the exact stress concentrations the original builders so ingeniously avoided. In the next earthquake, that modern mortar would become a network of fault lines, guaranteeing the wall's collapse. Conservation architects working with organizations like UNESCO advocate for a different philosophy, the principle of minimum intervention. The goal is to do only what is absolutely necessary to slow decay and ensure structural integrity, using materials and methods as compatible as possible with the original. This often means developing custom mortars that match the historic mix in strength, porosity, and, crucially, flexibility. In some cases, the solution is even more subtle, using sacrificial materials. These are new elements, like soft wooden pegs or weak mortar mixes, intentionally designed to fail before the ancient fabric does. They act as modern, replaceable fuses, absorbing damage in a controlled way during a seismic event, thereby protecting the irreplaceable historic stone. The work following the 1997 earthquakes in Umbria, Italy, provides in this careful approach. The Basilica of St. Francis in Assisi suffered devastating damage, with vaults collapsing and priceless frescoes shattered. The restoration team faced an immense challenge: to make the structure safe without turning it into a modern reconstruction. They employed a meticulous process of the careful reassembly of fallen elements using original materials wherever possible, but they went further. They integrated a hidden, state-of-the-art seismic isolation system beneath the basilica's foundations. Using advanced shock-absorbing technologies that function on the same principle as the ancient gravel beds we discussed earlier. This hybrid approach honored the past while securing the future, a respectful dialogue between 13th century faith and 21st century engineering. Not all interventions have been so successful. There are well-documented cases where overzealous restoration, using incompatible cement or intrusive steel reinforcements, has accelerated decay or created new structural vulnerabilities. These failures highlight a critical debate within conservation, the tension between the complete reassembly of a ruin to its former glory and stabilization, which simply secures the ruin in its current state. Reassembly can make a site more visually comprehensible and emotionally powerful, but it risks creating a pastiche, a modern idea of what the building looked like, potentially built with modern, rigid connections. Stabilization is often more archaeologically honest, preserving the authentic narrative of decay and survival, but it can leave a site looking like a crumbling puzzle. This modern application of ancient wisdom forces us into a role of profound humility. We are no longer just admirers of these stone giants, we have become their guardians. To care for them properly, we must first understand the language in which they were written. We must learn to distinguish between a crack that is a sign of fatal weakness and a joint that is designed to breathe. Every repair, every reinforcement, is a test of our comprehension. Are we listening to the whispers of the original builders, or are we shouting over them with our own assumptions of strength? The ethical dilemma ensures that the story of these monuments does not end with their construction. It continues today, in laboratories developing compatible mortars, in debates among international committees, and in the steady, careful hands of a conservator choosing the right mix for the right crack. In protecting these secrets, we are forced to become their students, applying lessons from a forgotten age with the greatest care our modern world can muster. The future of our cities could be written in the language of these ancient stones. Beyond museums and history books, the seismic secrets we have uncovered are now inspiring a quiet revolution in how we design for tomorrow. This is not about copying the past, but about learning its grammar, translating principles forged in stone into a new vocabulary for sustainable, resilient living. A new generation of architects and engineers are looking past the industrial age's reliance on steel and concrete, turning instead to the wisdom of biomimicry and the revival of vernacular building traditions. They ask a simple, profound question. What if our buildings could behave more like forests or mountains or those ancient, flexible walls? The answers are leading to a future where architecture works with natural forces, rather than fighting them with brute force. Consider the concept of the rocking wall, a direct descendant of the dry stone principle. Modern research facilities are testing concrete or composite walls designed with joints that allow them to rock on their foundations during an earthquake. Like a tree swaying in the wind, these walls lift slightly, then settle back into place, their motion dissipating energy through controlled friction. A structural engineer working on such a project recently noted, "We are not inventing something new. We are rediscovering a behavior that ancient masons observed and harnessed." The goal is to create structures that can weather a seismic event with minimal damage, ready for use again almost immediately, avoiding the colossal waste of a total rebuild. This thinking extends to entire buildings designed with base isolation systems that mimic the effect of a gravel bed foundation, or with facades that use interlocking. Prefabricated panels inspired by polygonal masonry creating a skin that can flex and absorb impact. The most promising applications merge this ancient logic with a commitment to ecological sustainability. The field of modern earthen architecture is experiencing a renaissance, driven by the need for low-carbon building materials. Architects specializing in rammed earth or compressed earth block construction are actively integrating seismic lessons from history. They are designing walls with internal timber lacing, creating flexible bamboo reinforcement grids, and shaping buildings with tapered, buttressed forms that channel forces safely into the ground. These structures use local soil, have superb thermal mass for natural temperature regulation, and their very composition often has a lower embodied energy than industrial materials. One visionary architect described it as building with the landscape, not just on it. This approach dramatically reduces reliance on energy-intensive steel and concrete, materials whose production is a major contributor to global carbon emissions. Even cutting-edge technology like 3D printing is looking backward for inspiration. Researchers are programming robotic arms to print cementitious structures with complex, interlocking geometries that would be impossible with traditional. These are not smooth, monolithic walls, but porous, lattice-like structures that distribute stress in organic, efficient patterns, echoing the load-sharing web of a polygonal wall. Other experiments involve creating buildings with tunable mass dampers inspired by the suspended pillars of ancient temples, or using phase-changing materials within walls that absorb heat and vibration, much like the thermal mass of a stone fortress moderates its internal climate. This convergence points toward a profound shift in philosophy. For over a century, modern architecture often sought to separate itself from nature, to create sealed, controlled environments. The ancient secrets suggest a different path, one of integration and dialogue. They teach us that resilience is not a product you bolt onto a design, but a quality that emerges from the entire system, from its geometry, its materials, and its connection to the site. The past becomes a living laboratory, not of outdated techniques, but of fundamental principles for enduring on a dynamic planet. In looking back to these stone giants, we are not retreating from the future, but finding a wiser, more grounded path forward, where our shelters are not just safe, but are themselves a testament to harmony. Archaeological soil holds a brutal kind of memory. Dig through the layers of a city in a land of tremors, and you will find a story told in broken stones and sudden change. One layer shows orderly streets and uniform houses, built in a style that had stood for generations. Then comes a thick, chaotic stratum of rubble, ash, and shattered pottery, the signature of a cataclysm. Above that, the story resumes, but the architecture is different. The walls are thicker, the corners are rounded, the foundations dig deeper. This is the 30th secret, the role of seismic events as ruthless, unforgiving teachers in the school of architectural evolution. Historians of disaster describe a pattern they call architectural punctuated equilibrium. For long periods, building traditions remain stable, passed down from master to apprentice with little change. Then a massive earthquake strikes, a punctuating event that shatters not just buildings, but assumptions. The old ways are tested at full, terrifying scale, and their failures are laid bare for all to see. This destruction creates a grim but clear slate, a societal imperative to rebuild, but to rebuild smarter. The period immediately following a major quake becomes a hotbed of frantic innovation, where new techniques are tried, refined, and adopted at a pace unthinkable during times of peace. It is evolution accelerated by catastrophe. We can trace this process in the ancient historical record. After a devastating quake shook the region of Sparta, The city's reconstruction reportedly incorporated new rules about building height and material strength. Some of the earliest hints of organized building codes born from direct experience. In Anatolia, the heart of the Hittite Empire and later a Roman province, cities leveled by tremors were often rebuilt with deliberate anti-seismic modifications. Archaeologists note the introduction of timber lacing in later phases of construction, or the strategic use of more flexible mortar mixes, clear responses written in stone to a lesson learned in rubble. The destruction event served as a city-scale laboratory, albeit a tragic one. Builders could walk through the ruins and perform a kind of forensic engineering. They saw which walls had pancaked and which had merely cracked. They observed how towers fell and which foundations held. This empirical data, gathered in the wake of immense hardship, was more valuable than any theory. It showed, in the starkest terms possible, what worked and what did not. A powerful example of this evolutionary leap can be seen in the domes of Persia. The early Sasanian Empire produced magnificent brick domes, like the Great Arch of, yet these vast spans were vulnerable to the region's frequent seismic shocks. The collapse of such monumental symbols was both a practical and a spiritual crisis. The response, developed over centuries of rebuilding, was a revolution in form and technique. Persian architects pioneered the use of the squinch, a clever architectural device that gracefully transitions a square room into a circular dome base, and began building double shells. They created outer and inner dome layers, often with a cushioning layer of loose brick or mortar between them. This was not just for grandeur, it was for survival. During an earthquake, the two shells could shift independently, the inner layer protected by the sacrificial movement of the outer. They also perfected the use of light, porous bricks and a special gypsum mortar that cured with a slight flexibility. Each major seismic event refined the recipe, leading to the sublime, earthquake-resistant domes of later Islamic architecture, like those in Isfahan, which have weathered centuries of tremors. This reveals a dynamic, almost dialectical relationship between civilization and the planet. The Earth's destructive power acts as a brutal editor, deleting failed designs from the architectural gene pool. Human creativity responds with a surge of adaptation, writing new solutions in mortar and stone. The process is not gentle, and its cost is measured in lost homes and cultural treasures. Yet, from this iterative dialogue between destruction and creation emerges a deeper, hard-won resilience. It shows that our most enduring innovations are often forged not in times of quiet comfort, but in the urgent, sobering silence after the ground has finally stopped shaking. A grand temple and a simple hut can share the same silent guardian. Across the ancient world, the most sophisticated seismic techniques were not the exclusive property of kings and priests. They flowed in a continuous loop between the monumental and the mundane, between the palace walls and the farmer's home. This interplay reveals a society where the knowledge of how to stand firm was a collective treasure, refined in the laboratory of daily life and elevated into stone legend. Ethnographers working in seismic hotspots from the Himalayas to the Andes have documented this living continuum. They observe master builders who can construct both a humble dwelling and a community temple, using the same core principles adapted to scale and resources. In a village in Nepal, a house might be built with a flexible timber frame and walls of woven bamboo filled with stone and mud, a technique that allows it to sway gracefully in a tremor. Just up the path, the village shrine incorporates the same braced timber skeleton, but its infill is finely carved stone, its proportions more monumental. The seismic logic is identical, only the materials and ornamentation differ. This suggests a powerful, decentralized model of innovation. The most effective solutions were often born from necessity, from countless generations of ordinary people observing what kept their families safe. A farmer might discover that adding a diagonal timber brace to his storage shed stopped it from collapsing during minor tremors. That practical insight, shared and refined across a valley, could eventually be scaled up and formalized by royal engineers into the timber lacing used in a fortress wall. It was a trickle-up of wisdom. Conversely, techniques perfected on monumental projects could trickle down. The precise leveling methods developed to lay a temple's foundation might be for use in a village, ensuring a house's stone plinth was perfectly flat and stable. The knowledge was fluid, moving along the social currents of craftsmen, laborers, and traveling builders who worked on both grand and humble projects. We can see this dialogue etched into the ruins of ancient cities. In Pompeii, before its volcanic end, the seismic story is told in its varied architecture. The grand villas of the wealthy often featured elegant ashlar masonry, cut stone blocks fitted with precision. But many common houses, or insulae, used a different, brilliant technique called opus. This involved building a framework of wooden posts and rails, then filling the panels with rubble and mortar. It was essentially Roman timber lacing, creating a lightweight, flexible cage that could withstand the region's frequent tremors. When the ground shook, the wealthy relied on the mass and precision of their stone, while the common people relied on the flexibility of their wood and rubble composite. Both approaches, born from different resources but the same need, survived side by side, a testament to a society with multiple answers to the same violent question. At Knossos on Crete, the great Memnon Palace complex itself shows this hybrid thinking. Its monumental walls are complemented by clever use of wooden columns and beams, creating a structure that was both imposing and dynamic. The same principles of flexibility and load distribution evident in the palace likely informed the construction of smaller surrounding buildings, creating an urban fabric woven with shared seismic sense. This democratization of resilience knowledge underscores its fundamental role. It was not merely an artistic or religious pursuit, it was a core technology for communal survival. When a society invests its collective intelligence into making every home, not just every temple, capable of enduring the earth's anger, it reveals a profound cultural priority. Safety was not a luxury reserved for the gods and their representatives. It was a shared right, a common skill passed from parent to child, from neighbor to neighbor. The grand monuments we marvel at today were not isolated triumphs of engineering, but the most visible peaks of a vast, lived-in landscape of wisdom. Where every humble wall that stood taught a lesson that would one day help a giant to never fall, a mountain does not wonder how it will stand, it simply does. This 30-second secret asks us to see the land not as a canvas for human genius, but as the original blueprint, the first and greatest teacher of stability. Before any stone was cut, the earth itself displayed the principles of endurance. Across the planet, natural formations have withstood eons of wind, water, and seismic force through a silent, perfect geometry of equilibrium. The balanced rock, the natural arch, the sheer cliff face of a mesa, these are not accidents, but demonstrations of nature's own structural logic. Geomorphologists who study these forms note that they survive because their mass is distributed in harmony, with the forces acting upon them. A talus slope, that apron of fallen rock at the base of a cliff, achieves a natural angle of repose where friction perfectly balances gravity, creating a stable, self-reinforcing shield. An arch transfers weight along its curving spine, channeling stress into the solid earth at its feet. Ancient builders, living in intimate daily observation of these landscapes, would have absorbed these lessons through their senses. They walked among titans that had never fallen. It is a compelling thought that the first seismic engineer was not a human, but a planet, and the first textbook was written in stone, water, and time. This leads to a profound shift in perspective. Perhaps the most resilient megalithic sites are not triumphs of human design imposed upon the landscape, but acts of profound mimicry. The builders may have been consciously echoing the forms that had already proven their worth against of turmoil. When they shaped a pyramid, were they idealizing the stable, triangular profile of a distant, sacred peak? When they constructed a massive, inward-leaning wall, were they replicating the sturdy base of a weathered mesa? This idea moves beyond simple symbolism. It suggests a technical observation, that the shapes which endured in the wild were the shapes most worthy of reproduction. The greatest secret was not inventing resilience, but recognizing it in the world around them and learning to speak its language in crafted stone. We can see this dialogue between natural form and human artistry in breathtaking clarity at sites that are not so much built as revealed. The rock-cut churches of in Ethiopia are not structures placed upon the earth, but sculptures carved from it. 11th century builders identified a massive seam of soft, red volcanic rock and carefully excavated it, leaving behind intricate churches, tunnels, and courtyards. These monolithic buildings are not sitting on bedrock, they are continuous with it. Their foundations are the living continent. In seismic terms, this is the ultimate stable base. An earthquake cannot settle a foundation that is not separate from the ground. It can only make the entire geological formation move as one. The builders here did not fight the mountain. They collaborated with it, uncovering a sacred space they believed was already present within the stone. Similarly, the breathtaking tombs of Petra in Jordan are facades carved directly into the rose-red sandstone cliffs. They did not quarry blocks and stack them. They studied the cliff's natural fractures and bedding planes, then chiseled their monumental architecture into the most stable sections of the rock face. The resulting structures are immune to the lateral forces that topple freestanding walls, because they are the wall, an integral part of the mountain's own skin. This approach displays a deep geological wisdom. By choosing to build within the earth rather than upon it, these cultures the entire problem of foundation failure and structural resonance. They let the planet's own monolithic mass do the work of stability. This secret ultimately reframes the ancient builders' role. They were not just architects or engineers, but keen students of geophysics. They spent generations learning to read the landscape, to identify which rock formations stood unshaken after storms and tremors, and which had crumbled into rubble. Their construction may have begun with a simple, reverent question: what has the earth itself already built to last? The answer, written in canyon walls and mountain spines, became their guiding principle. In the end, their most profound innovation might have been humility, the decision to listen to the stone and to build in harmony with its ancient, unshakable song. A simple clay pot filled with water could reveal the future of a city. Before the first foundation stone was laid, ancient builders engaged in a quiet, meticulous form of risk assessment. This was not the precise mathematics of a modern seismologist, but a profound, qualitative reading of the land, a search for whispers of past violence and future stability. The question is compelling: did these cultures possess a formal scale for seismic hazard? While they lacked our instruments, evidence suggests they developed a sophisticated system of observation, one that categorized land not by abstract risk percentages, but by the direct testimony of nature itself. Historians of ancient science point to remarkable records from China, where the role of earthquake predictor was a formal court position. These officials were tasked with observing anomalies, from unusual animal behavior and well water levels to subtle shifts in the ground. Their reports were not mere superstition, they were a systematic catalog of precursory signs, an early warning network built on generations of meticulous note-taking. In the Mediterranean, the placement of oracles like Delphi at geologically active sites is telling. The tremors and vapors issuing from the earth were not just atmospheric effects, they were considered the very breath of the divine, a clear signal that this was a place of powerful, unstable forces. Choosing to build a major religious center, there was not an oversight, it was an acknowledgement, a decision to engage directly with the planet's volatile energy. But to do so with structures engineered to withstand its expression. The practical methods for this pre-construction assessment were elegantly simple. A master builder might use a long, water-filled trench as a giant level, not just to flatten a site, but to detect any subtle, existing tilt in the bedrock, a possible sign of prior seismic displacement. They dug deep test pits to examine the soil strata, searching for layers of jumbled rock or sand that told stories of ancient landslides or liquefaction. They observed the landscape with a forester's eye. Trees growing with a pronounced lean or with strange, gnarled roots might indicate ground that was slowly, persistently creeping. A slope littered with fresh rockfall was a clear warning to build elsewhere. This environmental awareness directly guided the grandest decisions of state, the placement of entire cities. While they may not have mapped fault lines as we do, they intuitively avoided the most obvious hazards. The ruins of many ancient settlements show a clear pattern. They are set back from steep, unstable cliff faces, built on solid alluvial fans rather than directly in the floodplain, and positioned away from the stark, fresh scarps in the earth that scream of recent, violent movement. They chose the shoulder of the valley, not its trembling heart. This represents a seismic wisdom of a different kind, one of strategic avoidance and informed acceptance. It was a calculus that weighed the benefits of a location, its water, its defensibility, its spiritual significance, against the palpable risks written in the stones and the trees. They could not eliminate the hazard, but they could quantify it in the only terms that mattered to them, the lived experience of the landscape and the memory of their ancestors. This preemptive dialogue with danger ensured that when they finally chose to build, they did so on ground that had already passed the Earth's own brutal test of time, giving their engineered miracles the firmest possible stage upon which to perform their enduring, silent dance. The memory of a tremor can outlive the stones it shook. A grandmother's warning, a festival date on the calendar, a story told to children about why the old wall is cracked, these are not just folklore. They are the living architecture of a seismic culture, a society's collective memory of catastrophe woven directly into its rules for survival. This intangible force, the cultural trauma of past collapse, may be the most profound and enduring secret of all. Disaster anthropologists who study communities in earthquake zones observe a fascinating phenomenon. After a devastating event, the raw terror and loss do not simply fade, they crystallize. They become embedded in the very rituals and stories that define a people, transforming lived experience into a coded guide for future generations. This process ensures that hard-won technical knowledge is not stored in a library, but in the heartbeat of the culture itself. The memory dictates behavior in subtle, powerful ways. It creates taboos, unspoken laws that feel like ancient wisdom. A village might have a strict prohibition against building a home taller than 2 stories. On the surface, it might be explained as respecting the mountain spirits or keeping a humble profile, but the practical root is often seismic. An ancestor, centuries ago, witnessed a 3-story tower crumble and kill a family. That single, horrific image became a story, the story became a rule, and the rule became a sacred boundary. No one remembers the physics of harmonic resonance, but everyone obeys the taboo that keeps them safe. Similarly, prescribed practices emerge from this cultural memory. In parts of the Andes, there are communities that perform an annual ceremony of inspecting the mortar in their oldest communal buildings. It is framed as honoring the ancestors and renewing the bond with Mother Earth. Yet the practical outcome is a systematic, community-wide check for structural weaknesses. The ritual ensures maintenance happens not when a crack appears, but before it ever can. The calendar itself becomes a teacher. In Japan, the concept of the earthquake is not merely a geological term. It is a deep cultural presence, reflected in everything from woodblock prints depicting great tremors to the design of everyday objects. This awareness is not born from fear alone, but from a refined aesthetic of impermanence and resilience. The traditional Japanese house, with its lightweight materials and flexible joints, is a philosophical response to a volatile earth, a physical expression of the understanding that nothing is rigid forever. The memory also shapes foundational myths. Stories of a great flood or a time when the mountains walked are common across seismic regions. These are often interpreted as metaphors for social upheaval. But they also serve as durable containers for traumatic geological truth. The myth provides a safe, symbolic way to talk about the unspeakable, the ground turning to liquid, the deafening roar of splitting rock. By ritualizing the catastrophe, the culture gains a measure of control over it. They rehearse the narrative of survival every time the story is told. This cultural memory acts as a slow, burning fuse for innovation. It creates a societal patience for techniques that may seem overly complex or time-consuming. Why would a culture spend generations fitting polygonal stones with impossible precision? Because the oral histories, the songs, the very bones of their oldest poetry tell them that the rectangular walls of their forefathers fell, and the people within them did not rise. The extra labor is not a burden. It is an offering to memory, a direct answer to the ghosts of the last great quake. When that memory fades, when generations pass without a major tremor, something dangerous can happen. Engineers call it seismic amnesia. The taboos begin to feel like superstition. The prescribed practices seem like pointless tradition. The drive to build taller, faster, and cheaper overrides the ancient, whispered warnings. This is often when the greatest losses occur, not when knowledge is absent, but when the cultural vessel built to carry it is broken. The final, invisible pillar holding up these ancient wonders was not stone or wood, but story. It was the unbroken chain of memory that connected the mason's hand to the grandfather's tale, ensuring that every block laid was a reply to an old question asked by the trembling earth. These silent stone giants have spoken across the ages, their language one of profound endurance. From the jigsaw walls of the Andes to the swaying pagodas of Japan, the seismic engineering secrets hidden inside ancient megalithic architecture reveal a profound dialogue between humanity and a dynamic planet. Our journey has explored 34 facets of this enduring mystery, uncovering principles of flexibility, mass, geometry, and even cultural memory that granted these structures a kind of immortality. We have seen that resilience is not a single trick, but a complex, layered conversation. It is the friction in a dry stone joint, the inertia of a pyramid anchored to bedrock, the harmonic scattering of a polygonal wall, and the sacred story passed down to remind a community how to care for its home. These monuments are not mere artifacts of a primitive past, but sophisticated textbooks written in stone, each chapter offering a timeless lesson in how to stand firm when the world shakes. They challenge our modern assumptions about strength, showing us that true durability often lies in the ability to yield, to adapt, and to harmonize with forces far greater than ourselves. As we face a future defined by climate uncertainty and dense urban landscapes, these ancient secrets offer more than historical curiosity. They present a vital challenge to our own era. They ask us to build with a new kind of wisdom, one that embraces humility over hubris. Can we design our cities not to conquer nature, but to engage in a thoughtful dialogue with it? Can we create structures that are not just strong, but intelligently resilient, capable of bending without breaking and enduring for generations without consuming the earth? The principles we have uncovered, distributed strength, redundant systems, and deep integration with sight, are not locked in the past. They are a living legacy, a toolkit for a more sustainable and stable future. Let these silent teachers inspire your own curiosity. Look at the old stone walls in your own region, the traditional buildings in your heritage. What forgotten wisdom might be embedded in their shapes, their materials, their very placement? The dialogue between humanity and a restless planet continues, and we are all part of it. We would love to hear which secret from our exploration fascinated you the most. Was it the living flexibility of dry stone, the cosmic geometry of sacred plans, or the powerful memory held within cultural stories? Share your thoughts in the comments below. If you enjoyed this journey into the hidden intelligence of the past, subscribe to join us as we continue to decode the profound mysteries of our world. The past, it seems, still has much to teach us about standing firm.